Hello there and welcome to Simply About Earth, where curiosity finds its quiet corner and wonder takes its time. Before we begin tonight's journey, I'd love to know, drop a comment and tell me where you're watching from. Whether you're tucked into bed in Tokyo watching the sunrise in Sao Paulo, or taking a break somewhere in between, it's always fascinating to see how far these questions travel. Tonight, we're going to follow a thread, not one with easy answers or clean edges, but one that invites us to think differently about the ground beneath our feet, the air we breathe, and the intricate dance of systems that keep everything moving. What if Earth wasn't just a lucky accident? What if, and I mean this as exploration, not doctrine, what if our planet shows signs of something more intentional than pure chance? Now, I don't mean designed in the sense of cosmic blueprints spread across some celestial drafting table, though the image of universal architects with their slide rules is admittedly charming. I mean something broader, deeper. The possibility that Earth's remarkable suitability for life reflects patterns, principles, or processes that tend toward order rather than chaos. Whether you picture that as intelligent guidance, emergent complexity, natural algorithms, or something else entirely, well, that's part of what we'll explore together. This isn't about proving or disproving anything. That's not the pace we keep here on Simply About Earth. We're not rushing toward conclusions or planting flags on definitive answers. Instead, we're taking a slow walk through the landscape of possibility, noticing the small details and the grand patterns, letting questions breathe and expand. Because sometimes the asking matters more than the answering. Sometimes the journey teaches us more than any destination ever could. So settle in, let your mind wander where it will, and let's begin with the simple, profound act of paying attention. Think about your ordinary day. Really think about it. You wake to light streaming through your window, not the harsh radiation that would fry organic molecules, but a gentle spectrum filtered through an atmosphere that blocks the worst while letting through the best. The temperature isn't scorching or freezing. It's within the narrow band where liquid water can exist, where proteins can function, where life as we know it can unfold. You take a breath, and the air is there, waiting. Roughly 21% oxygen, enough to fuel your cells without poisoning them, mixed with 78% nitrogen to dilute the reactive oxygen and provide essential nutrients for plant growth. You get thirsty and water flows from the tap, clear, tasteless, essential, delivered through systems that purify and transport it from distant sources. Maybe you step outside. The gravity pulls at you with exactly the right force, strong enough to hold an atmosphere, gentle enough that you can walk upright without being crushed. Plants photosynthesize in the sunlight, converting carbon dioxide to oxygen in a planetary respiratory system. Animals move through ecosystems where predators and prey, decomposers and producers all fit together in intricate webs of relationship and exchange. Everything seems to line up, not perfectly, but remarkably well, well enough to support not just survival, but complexity, diversity, even consciousness capable of reflecting on its own existence. It's easy to take all this for granted. Most of us do, most of the time. But underneath that comfortable familiarity lies something worth pausing over, something that invites deeper consideration. Is this all coincidence? Could it be, or does it feel like pieces in a puzzle that fit together a little too well to be entirely random? Science has mapped out the mechanisms, and what detailed, elegant mechanisms they are. We understand planetary formation, stellar evolution, atmospheric chemistry, biological development. The frameworks are robust, tested, predictive. We can trace timelines that stretch across billions of years, model processes that shape worlds, explain how complex systems emerge from simpler components. And yet, even within these scientific frameworks, there are things that make people pause, patterns that seem, frankly, a bit too convenient for a universe governed purely by blind chance. Consider Earth's position, orbiting a remarkably stable star in what astronomers call the habitable zone, the Goldilocks region where water can exist as a liquid. That alone might seem fortunate, but the fine-tuning goes much deeper. The planet's tilt gives us seasons without extremes. Its rotation speed keeps temperatures from swinging too wildly between day and night. The moon's size and distance stabilize that tilt and create tides that may have been crucial for early life. The presence of a magnetic field shields us from solar radiation that would otherwise strip away our atmosphere. The mix of gases in that atmosphere maintains temperatures and chemical conditions within livable ranges. The balance of land and ocean, the cycling of carbon and water, the slow drift of continents that creates geographic diversity. You can keep going. Each of these factors could have been different, wildly different, and if they were, life as we know it might never have appeared. Some call this the anthropic principle, the idea that of course the universe looks suited to life because we're here to observe it. If it weren't suited to life, we wouldn't be around to ask these questions in the first place. It's a tidy explanation in one sense, but it doesn't stop the wondering. Is it really enough to say, well, we're here, so it must have worked out somehow, or does that sidestep something deeper, something that deserves more careful attention? Patterns don't prove purpose. That's important to acknowledge up front, but they can point toward it, or at least make it worth considering. So what we're going to do is examine these patterns, not as believers or skeptics, but as explorers. We'll wander through the clues and coincidences, the physics and philosophy, the mathematics and metaphors, and we'll do it slowly, without needing to land on any single conclusion. Because whether Earth was designed or not, it behaves in ways that often feel as if it were. That's not a claim. It's an observation, an invitation to ask what would be different if it were designed, what would stay the same, and what might that tell us about the nature of reality itself. To explore this properly, we'll need to go both wide and deep. We'll talk about planetary physics and stellar astronomy, biology and chemistry and geology, but we'll also talk about perception and meaning, about why humans seem drawn to finding intention in pattern, purpose in process. Some of that impulse might come from religious tradition, certainly, but not all of it. The urge to look at the sky and feel that it means something is older than any sacred text, deeper than any doctrine. Take something as basic as our response to symmetry. We're drawn to it. In faces, flowers, crystals, galaxies, when we encounter symmetrical forms, something in our brains responds with recognition, even pleasure. We find them beautiful, harmonious, right. That preference might not prove anything metaphysical, but it's a starting point. Why should a universe formed by random processes keep producing forms that appeal to our sense of order? Why does our notion of beauty align so often with what turns out to be mathematically elegant, functionally efficient? This is where things get interesting, because even if you start from a purely materialist worldview, you still end up swimming in questions that sound philosophical. The more we learn about biology, for instance, the more we discover systems of breathtaking precision, from protein folding to DNA replication to cellular communication. It's all specific, interdependent, often inexplicably efficient. Not perfect, mind you. Evolution is messy, full of kludges and compromises. The body carries plenty of quirks and evolutionary baggage, but it works astonishingly well, and in ways that sometimes resemble what we might call engineering. Not human engineering necessarily, but systematic organization toward functional outcomes. The word design is loaded. It tends to conjure images of a conscious designer sketching blueprints or tweaking parameters, but it doesn't have to mean that. Design can also refer to structure, organization, pattern that emerges not randomly but with direction, even if we don't know the source of that direction. The idea that Earth might be designed doesn't necessarily require a specific designer. It could point towards something more abstract, a universe governed by deep principles that naturally yield life-supporting outcomes. Or it could suggest selection rather than construction, that out of many possible worlds, this one happened to support complexity and consciousness. And so here we are to notice it. But that raises another intriguing question. How many possible Earths are there? Are we the fortunate one in a trillion? Or is the universe teeming with worlds like this, each with its own version of stability and strange beauty? We don't know yet, but as we discover more exoplanets, thousands so far, we're beginning to see just how rare or common Earth-like conditions might be. And the preliminary answer is, we seem to be unusual, not impossible, not singular, but certainly not typical. We've found planets too hot and too cold, too big and too small, too dense and too gaseous, worlds without atmospheres, and worlds with crushing atmospheres, planets orbiting stars that flare violently, systems too young for stability, orbits too elliptical for consistent climate. The more we look, the clearer it becomes that Earth occupies a rather special place in the spectrum of planetary possibilities. Of course, special is hard to define in a universe this vast. Maybe the apparent rarity of Earth-like conditions is exactly what we'd expect from a system governed by chance. Most lottery tickets lose, but somebody has to win. Or maybe it suggests something else, some bias in the cosmic deck toward outcomes that support complexity, consciousness, the capacity to ask questions about existence itself. There's another dimension to consider: time. Not just location in space, but timing in the cosmic story. Life didn't just need the right ingredients and conditions, it needed them in the right sequence, sustained across billions of years. A stable planetary environment, yes, but also relatively calm cosmic weather. Not too many asteroid impacts, not too many stellar flares, enough geological activity to cycle nutrients without constant catastrophe. The timing had to align, and not just once but repeatedly, across scales from seconds to eons. The formation of complex molecules, the emergence of self-replication, the development of photosynthesis, the oxygenation of the atmosphere, the evolution of multicellular life, the rise of intelligence. Each transition required conditions that persisted long enough for the next level of organization to stabilize. That's not impossible by any means, but it's another piece in a growing puzzle of apparent coordination. People explain this convergence in different ways. Some see divine providence. Others see statistical inevitability given enough time and space. Still others see emergent properties of self-organizing systems, complexity arising naturally from the interaction of simple rules. But the idea that Earth might represent intentional arrangement, whether through direct action or through deep structural principles embedded in natural law, remains compelling. Not because it's provable, but because it continues to align with our lived experience of a world that feels built for inhabitation, discovery, even wonder. We are, after all, creatures who build things. We plan, imagine outcomes before they happen, design systems to achieve specific goals. So when we encounter a world that seems built just so, it's natural to wonder whether something planned it, whether intelligence, in some form we might not recognize, preceded the intelligence we're familiar with. Still, we have to be careful. Patterns can emerge from randomness. We see it in computer simulations all the time. Perception can mislead us into seeing intention where only process exists. Just because something feels designed doesn't mean it was. Just because an outcome seems improbable doesn't mean it was planned. But the flip side is equally true. Just because science can explain how something happened doesn't mean we fully understand why it happened the way it did, or whether there might be deeper organizing principles at work. The mechanisms of evolution don't preclude the possibility that evolution itself operates within a framework that favors certain kinds of outcomes. So the question we're exploring, what if Earth was designed, isn't about disproving science or proving belief. It's about holding a space where both can ask the same fundamental questions from different angles. How do we account for the remarkable suitability of our world for life? What does that suitability tell us about the nature of reality? And how should we live in light of that uncertainty? As we continue, we'll examine specific aspects of Earth that often come up in this conversation: the orbital dynamics that keep us at just the right temperature, the Moon's peculiar role in planetary stability, the atmospheric balance that supports complex chemistry, The intricate machinery of biological systems, the mathematical patterns that show up in both living and non-living structures. Each of these opens up its own set of questions, not only about science, but about what we expect from reality itself. When we ask whether Earth was designed, we're not just wondering about planets and physics, we're probing something more personal, how we understand our place in the universe, whether life represents accident or intention, whether the world is a series of coincidences, or part of something that was meant to be exactly as it is. That's why this question feels different from other scientific topics. Ask about volcanic formation or seasonal cycles, and you get interesting but emotionally neutral information. Ask whether Earth might have been made on purpose, and you're stepping into territory that humans have been exploring since they first looked up at the stars and wondered what it all means. It's the kind of question that shows up in philosophy and religion, in myths and stories about worlds shaped by hands or voices or dreams. While these traditions differ dramatically in their details, they share something important. They reflect a deep human instinct to connect what is with what means something, to transform facts into purpose. That instinct isn't something to dismiss casually. It's tempting to assume that science and meaning occupy separate domains, that one tells us how and the other tells us why, with a clear boundary between them. But the line isn't always so clean. The more we understand about how the universe works, the more we notice moments where structure and outcome converge in ways that feel guided might be too strong a word. Let's say directed, intentional, as if the rules themselves favor certain kinds of results. Take something as fundamental as carbon, the element that forms the backbone of all known life. Carbon is remarkably versatile. It bonds easily with other elements, forms long chains and complex shapes, creates stable molecules that can store information and catalyze reactions. Without carbon chemistry, life as we know it simply wouldn't work. And when you trace how carbon comes into existence, you realize it's the product of very specific conditions inside stars, nuclear fusion processes that require precise balances of temperature, pressure, and timing. If the physics of stellar nucleosynthesis were slightly different, if the strong nuclear force were a bit stronger or weaker, if certain energy levels in carbon nuclei were offset by small amounts, the universe might be full of hydrogen and helium, but no carbon. No carbon, no complex chemistry. No complex chemistry, no life. No life, no observers to puzzle over cosmic fine-tuning. That kind of apparent precision makes people pause, not because it proves anything definitive, but because it illustrates how narrow the parameters seem to be, how specific the conditions that allow for complexity, consciousness, the capacity to reflect on existence itself. The more we learn about fundamental physics, the more it appears that many of the values that govern reality, the masses of particles, the strengths of forces, the expansion rate of space itself, had to fall within very tight ranges for complex matter to exist at all. Not just life, but stars, planets, atoms, chemistry, the basic infrastructure of an interesting universe. This observation has led to what physicists call the fine-tuning problem. Why these numbers? Why this version of reality rather than any of the countless other possibilities? There are several proposed solutions, none entirely satisfying, all requiring leaps of different kinds. One approach is the multiverse hypothesis, the idea that there might be countless universes, each with its own set of physical constants. In that scenario, we find ourselves in a life-supporting universe, simply because only life-supporting universes produce observers. It's a selection effect. We don't observe the sterile universes because there's nobody there to do the observing. That could explain the apparent fine-tuning without requiring any kind of design, but it comes with costs. We have no direct evidence for other universes, and the hypothesis raises new questions about what generates the multiverse and why it should produce the particular range of possibilities it does. Another approach suggests that these seemingly arbitrary constants might not be arbitrary at all, that they could emerge necessarily from some deeper theory we haven't discovered yet. That would make the fine-tuning less mysterious, but it would still leave us wondering why the deep theory itself has the form it does, why it yields a universe capable of supporting complexity. Either way, we're looking at a reality where things had to be a certain way, and they are. That raises the deeper version of the question, not just why Earth is the way it is, but why anything exists at all with these particular characteristics. Why should there be a universe with rules and patterns and relationships that allow for stars, planets, chemistry, biology, consciousness? That's a question no telescope can answer directly, and yet it lurks beneath every scientific discovery, every new understanding of how the world works. We keep peeling back layers of mechanism, only to find deeper layers that require their own explanations. And at some point, explanation reaches its limits, and wonder takes over. It's important to note that science doesn't require purpose to function. You can study gravity without believing it was created by an intelligence. You can map genetic codes without asking who wrote them. Science operates perfectly well in a framework of pure mechanism and chance. But science doesn't forbid questions about purpose either. It just doesn't depend on them for its methods or predictions. And for many people that leaves space for what you might call a middle path, a way of exploring the world through evidence and experimentation while remaining open to the possibility that there's more going on than mechanism alone can capture. This is where the design perspective enters the conversation, not necessarily as a replacement for scientific explanation, but as a lens for interpretation. It doesn't say we should stop investigating when something appears fine-tuned. It says the fine-tuning itself might be significant, might point toward principles or processes that we don't yet understand, but that shape the emergence of complexity. Of course, not everyone agrees on what those deeper principles might be. Some envision a conscious designer, a divine intelligence with intentions and goals. Others imagine built-in properties of existence itself, not a person, but a process that naturally tends toward order, beauty, functional complexity. Still others see design as a projection, something humans impose on patterns because we're evolved to find agency and intention in our environment. In this view, the appearance of design tells us more about human psychology than about the universe itself. Each perspective has merit, and in a sense they're all dealing with the same fundamental observation. The universe, and particularly our corner of it, exhibits types and degrees of organization that invite explanation. Whether that explanation involves intention or emergence, divine action or natural law, conscious design or unconscious selection, the underlying phenomenon remains. We live in a reality that supports not just existence but reflection on existence, not just matter but minds capable of understanding matter. Think about that for a moment. We are arrangements of atoms that have become aware of atoms, biological systems that can model other biological systems, products of evolution that can trace evolutionary history. The universe has become conscious of itself, at least locally, at least partially, and that consciousness can now contemplate its own origins and nature. Why should the universe be comprehensible to minds that evolved within it? Why should beings shaped by the need to find food and avoid predators develop the capacity to understand quantum mechanics, map genetic codes, probe the cosmic microwave background radiation? Albert Einstein once remarked that the most incomprehensible thing about the universe is that it's comprehensible. The laws that govern galaxies can be written in equations short enough to fit on a t-shirt. The same mathematical principles that describe planetary motion also govern atomic structure. Patterns that emerge in biology echo patterns found in physics, chemistry, even human-created art and music. That deep mathematical regularity could be coincidence, or it could suggest that mind and cosmos share some fundamental relationship. Not necessarily that the universe was made for minds, but that minds and the universe they inhabit operate according to compatible principles. This isn't a claim, just a thought worth holding. As we continue our exploration, in the end, these questions don't have to be threatening to a scientific worldview. If anything, they show how science can lead us right up to the edge of mystery and then keep going. You don't need to answer every question for the inquiry itself to be valuable. Sometimes the most important thing is just holding the question, letting it work on you rather than working on it. And this particular question, whether the world shows signs of intention, direction, design, is one of the oldest and most persistent that humans ask. But it's also thoroughly modern because now we have tools to examine the details more closely than ever before. We can study the building blocks of matter, map the forces of nature, trace the dynamics of biological systems, model the behavior of planetary atmospheres and stellar evolution. And as we do, the question doesn't go away. If anything, it deepens. Not because we're running out of explanations, but because the explanations themselves are so precise, so delicately balanced, so intricately interconnected, that they make you pause and wonder, is this all just what happened to work? Or does it reflect something more, not necessarily supernatural, but perhaps natural in ways we don't yet understand? Principles of organization that favor complexity over simplicity, information over chaos, the emergence of observers capable of appreciating what they observe? We can't answer that definitively. Not yet. Maybe not ever. But we can keep asking, keep following the structure and order and mathematical beauty wherever it leads, not to prove anything in particular, but to understand, and maybe in the process to glimpse something of what lies at the heart of it all. When we shift our attention from Earth's place in the cosmos to Earth itself, its structure, systems, the materials and processes that make up its substance, we encounter patterns that can feel oddly intentional. Some are geological, some chemical, some biological, but all of them seem to participate in a kind of planetary organization that goes beyond what you might expect from random assembly. Start with the basics. The planet's internal structure. Earth isn't just a solid ball of rock, it's layered, differentiated, dynamically organized. At the center lies a core of iron and nickel, divided into solid inner and liquid outer regions. The movement of that liquid metallic core generates Earth's magnetic field through a process called the geodynamo, a planetary dynamo that creates an invisible shield protecting the surface from solar and cosmic radiation. Without that magnetic field, charged particles from space would gradually strip away our atmosphere, as appears to have happened on Mars. The fact that Earth maintained its protective magnetic envelope for billions of years, that's not a given. It requires the right size, large enough to retain internal heat, the right composition, enough metallic elements, the right rotation rate, fast enough to stir the core but not so fast as to destabilize surface conditions. Above the core lies the mantle, hot, slowly flowing rock that drives plate tectonics. Those shifting crustal plates don't just reshape the surface, they regulate global climate by controlling the carbon cycle. When volcanoes erupt, they release carbon dioxide into the atmosphere. When mountains weather, they pull carbon dioxide back out. When ocean floors spread and subduct, they transport carbon between surface and interior. It's a planetary thermostat that operates over geological time, crude by engineering standards, but effective at maintaining temperatures within a range compatible with liquid water. The crust itself, that thin skin where all surface life exists, contains the chemical elements that biology requires, and in proportions that make complex chemistry possible. Carbon, nitrogen, oxygen, phosphorus, sulfur, calcium, the periodic table of life. These elements didn't all originate with Earth's formation. Many arrived later, delivered by asteroids and comets during what's called the Late Heavy Bombardment, a period when the inner solar system was showered with impacts that could have sterilized any emerging life or provided the building blocks that made life possible. The timing and intensity of that bombardment seems to have been just right, enough to deliver essential materials without completely disrupting planetary development. Too many impacts, and the surface might never have stabilized. Too few, and Earth might have lacked the chemical diversity that life requires. Even something as ordinary as soil reveals layers of fine-tuned relationships. Soil isn't just dirt, It's a complex mixture of mineral particles, organic matter, water, and air, all in proportions that support plant growth. Too much sand and water drains away too quickly. Too much clay and roots can't penetrate or breathe. The best agricultural soils strike a delicate balance, and that balance has to be maintained through constant cycling of nutrients, moisture, microscopic organisms. Plants and soil co-evolve, each shaping the other. Root systems prevent erosion while extracting nutrients. Fallen leaves decompose to enrich the mineral matrix. Mycorrhizal fungi form partnerships with plant roots, trading nutrients for carbon compounds. The system is self-organizing, but the fact that it organizes towards states that support diverse productive ecosystems rather than towards sterile equilibrium is worth noting. Consider something as basic as a seed. It contains everything needed for a new organism: genetic instructions, stored energy, protective coating, mechanisms for detecting the right conditions to germinate. When those conditions align, moisture, temperature, light, soil chemistry, the seed transforms. Roots grow downward, following gravity and chemical gradients. Shoots grow upward, seeking light. The whole process is exquisitely timed and coordinated, not consciously, but with a precision that resembles conscious planning. The shapes of seeds themselves seem optimized for distribution. Some are designed to stick to fur or feathers. Others have wings or parachute structures for wind dispersal. Still others are hard enough to survive passage through animal digestive systems, spreading when they're deposited with ready-made fertilizer. Each design fits its ecological niche, too well to feel entirely accidental. You see this same apparent optimization throughout biology. The fractal branching of trees that maximizes surface area for photosynthesis while minimizing structural material. The hexagonal patterns of beehives that provide maximum storage with minimum wax. The spiral arrangements of leaves and scales that pack efficiently while ensuring each element receives adequate light. These aren't random configurations. They follow mathematical rules, the same geometric principles that show up in crystals, river networks, lightning patterns, even galaxy formations. It's as if nature has a grammar, a set of preferred solutions that emerge wherever similar problems need solving. Some of this can be explained through evolutionary optimization. Traits that improve efficiency get selected and refined over time. But that explanation requires starting materials that can be optimized. It needs the chemical and physical properties of carbon, hydrogen, oxygen, nitrogen to allow for the formation of complex, stable, replicable molecules in the first place. And when you examine those properties, you find another layer of apparent fine-tuning. Water, for instance, has a remarkable collection of characteristics that make it ideal for biological processes. It's a powerful solvent, capable of dissolving more substances than almost any other liquid. It has a high specific heat, so it can absorb and release large amounts of energy without dramatic temperature changes, perfect for thermal regulation in living systems. Most unusually, water expands when it freezes, making ice less dense than liquid water. That means ice floats, and that seemingly trivial fact has enormous consequences. It means lakes and oceans freeze from the top down, creating insulating layers that protect life underneath. It means frozen water doesn't sink and disrupt established ecosystems. It's a rare property among chemical compounds, and one that turns out to be essential for maintaining habitable conditions through ice ages and seasonal cycles. Then there's the angle between hydrogen and oxygen atoms in the water molecule, 104.5 degrees. Change that angle slightly, and water's properties change dramatically. Its solvent capabilities, its thermal characteristics, its behavior at the molecular level, all depend on that specific geometric relationship. Why should the fundamental structure of matter yield a molecule so perfectly suited for complex chemistry? You could ask the same question about carbon's bonding properties, oxygen's role in energy metabolism, nitrogen's contribution to protein structure. Each element behaves in ways that seem almost designed to support the chemistry of life. Not exclusively, these same elements participate in countless non-biological processes, but the overlap between what chemistry allows and what life requires is remarkable. This convergence shows up at larger scales too. The Earth's rotation rate gives us days long enough for substantial photosynthesis, but short enough to prevent extreme temperature swings. The planet's axial tilt creates seasonal variation without wild climate swings. The Moon's distance produces tides large enough to create dynamic coastal environments, but not so large as to flood continents. Even the distribution of land and water seems conducive to biological diversity. About 30% land, 70% ocean, enough dry surface for terrestrial evolution, enough water for climate moderation and marine ecosystems, continents large enough to support diverse habitats, but not so large as to create vast, inhospitable interiors, mountain ranges that create rain shadows and climate zones, but not so extreme as to block all air circulation. You can frame all of this as a series of fortunate coincidences, and that's a perfectly reasonable perspective. In a universe large enough and old enough, unlikely combinations of favorable conditions are bound to occur somewhere. We observe this particular combination because we're the products of it, a selection effect rather than evidence of intention. But there's another way to look at it, as evidence that the underlying principles governing matter and energy naturally tend toward organization, complexity, the emergence of systems that can sustain and reproduce themselves, not through conscious planning, but through what you might call built-in preferences for certain kinds of outcomes. From this perspective, Earth isn't just a lucky accident. It's an example of what matter does when given appropriate conditions and sufficient time. It self-organizes. It complexifies. It develops feedback loops that maintain stability while allowing for change and growth. It creates the conditions for its own continuation and elaboration. Whether you call that design depends on how you define the term. It's not blueprint and construction design, but it's not purely random either. It's pattern formation according to rules that seem to favor the emergence of systems complex enough to contemplate their own existence. In our solar system, Earth sits in what astronomers call the habitable zone, the orbital region where temperatures allow liquid water to exist on a planet's surface. It's a concept that sounds precise but turns out to be surprisingly complex. The zone isn't fixed. It depends on the star's brightness, the planet's atmosphere, even the planet's geological activity. And being in the zone doesn't guarantee habitability, it just provides a necessary starting point. Earth orbits a G-type star, what we call the Sun, at an average distance of about 93 million miles. That sounds arbitrary, but it's not. A bit closer and we'd face a runaway greenhouse effect like Venus. A bit farther and we'd freeze like Mars. The margin isn't huge, maybe 5% in either direction before conditions become hostile to complex life. But distance is just one factor. The Sun itself had to be the right kind of star, massive enough to burn steadily for billions of years, but not so massive that it burns out quickly or produces lethal radiation. Stars much larger than the Sun have lifetimes measured in millions of years, not nearly enough time for complex life to evolve. Stars much smaller can be stable for trillions of years, but they tend to flare unpredictably, and their habitable zones are so close that planets get tidally locked, one side always facing the star, one side always dark. G-type stars like the Sun represent a sweet spot, about 10% of all stars in the galaxy. They're stable, long-lived, and produce energy across a spectrum that penetrates atmospheres without being destructive to organic molecules. The Sun has been burning steadily for about 4.6 billion years, and should continue for another 5 billion, a time span that brackets the entire history of complex life on Earth. But even being the right distance from the right kind of star isn't enough. Earth's orbit is nearly circular. Its distance from the Sun varies by only about 3% throughout the year. That minimal variation means we receive relatively constant solar energy, avoiding extreme seasonal temperature swings. Many exoplanets we've discovered have highly elliptical orbits that would create severe climate variations as they swing closer to and farther from their stars. The planet's rotation axis is tilted about 23.5 degrees relative to its orbital plane, enough to create seasons but not so much as to cause extreme variations. Without that tilt, there would be no seasons at all. Equatorial regions would be permanently hot, polar regions permanently frozen. Too much tilt and the seasonal swings would be so severe that large regions would alternate between being scorched and frozen. That tilt is stabilized by the Moon, another apparent piece of fortune. Without a large satellite, Earth's axial tilt would vary chaotically over geological time due to gravitation's perturbations from other planets. The climate would shift unpredictably between different states, sometimes ice ages, sometimes hot periods, sometimes rapid oscillations that would make it difficult for ecosystems to adapt. The Moon also drives Earth's tides, and those tides may have played a crucial role in the origin of life by creating oscillating wet-dry cycles in coastal environments. The rhythmic exposure and flooding could have concentrated organic molecules and promoted the chemical reactions that led to self-replicating systems. Even today, tidal ecosystems are among the most productive on the planet, rich interfaces between terrestrial and marine environments. Most other planets in our solar system lack moons large enough to significantly affect their rotation, and the few large moons that do exist orbit gas giants where surface conditions are dominated by crushing gravity and intense radiation. Earth's moon is unusually large relative to its planet, about 1/4 Earth's diameter, compared to moons elsewhere that are typically much smaller fractions of their parent planets. How did we end up with such an oversized satellite? The leading theory involves a Mars-sized object colliding with the early Earth and blasting material into orbit that eventually coalesced into the Moon. That scenario requires very specific conditions. The impactor had to be the right size, traveling at the right speed, hitting at the right angle. Too small and no Moon forms. Too large and Earth gets destroyed. Wrong angle and the debris either escapes or crashes back down. Even if that collision happened as theorized, the resulting system had to stabilize into a configuration that would remain stable for billions of years. The Moon had to end up at the right distance, close enough to stabilize Earth's rotation, but far enough away to avoid tidal catastrophes. And it has been slowly spiraling outward ever since, gradually reducing its gravitational influence, but slowly enough that Earth's climate has remained relatively stable throughout the age of complex life. Mars provides a sobering comparison. It sits just outside the habitable zone, cold, but not impossibly so. It has ice caps, seasonal variations, even dust storms that resemble weather, but it lost most of its atmosphere billions of years ago, probably because its magnetic field failed when its core cooled. Without magnetic protection, solar wind gradually stripped away the gases that might have maintained warmer surface conditions. Venus shows what can go wrong on the inner edge of the habitable zone. It's similar to Earth in size and composition, but its thick carbon dioxide atmosphere creates a runaway greenhouse effect. Surface temperatures reach nearly 900 degrees Fahrenheit, hot enough to melt lead. Its atmospheric pressure is 90 times Earth's. Rain falls as sulfuric acid. It's a reminder that being in the habitable zone isn't enough. Atmospheric composition and evolution matter just as much as orbital distance. Mercury and the gas giants are clearly unsuitable for life as we know it. Too hot or too cold, lacking solid surfaces bathed in radiation. But they play indirect roles in Earth's habitability. Jupiter, in particular, acts as a gravitational vacuum cleaner, capturing or deflecting comets and asteroids that might otherwise impact Earth. Its massive presence helps maintain stable orbits throughout the solar system. The asteroid belt between Mars and Jupiter represents another piece of apparent cosmic organization. If Jupiter were absent or differently positioned, that material might have formed another planet or might have been scattered into Earth-crossing orbits. Instead, it remains mostly confined to a stable region where it poses minimal threat to inner planet development. When astronomers look for potentially habitable exoplanets, they focus on systems that resemble ours, single stars of the right spectral type, with rocky planets in stable, roughly circular orbits within the habitable zone. Those criteria sound simple, but they're actually quite restrictive. Most star systems don't match them. Many stars exist in binary or multiple systems where gravitational interactions make stable planetary orbits difficult. Many planets are gas giants unsuitable for surface life. Many have been knocked into eccentric orbits by gravitational encounters. Many orbit stars that are too young, too old, or too unstable. Current estimates suggest that planets meeting basic habitability criteria might be rare, perhaps 1 in 1,000 star systems, maybe 1 in 10,000, and that's just for basic requirements, like liquid water. Add in factors like magnetic fields, large moons, plate tectonics, atmospheric composition, and habitable worlds like Earth become genuinely exceptional. Of course, rare doesn't mean impossible, and the galaxy contains hundreds of billions of stars. Even if Earth-like planets occur in only one system out of a million, there could still be hundreds of thousands of them in our galaxy alone. But we haven't found any yet, and the more precisely we understand what makes Earth suitable for complex life, the more special our situation appears. That specialness could be an observational bias. We notice Earth's unusual properties because we're here to notice them. But it could also suggest that the emergence of complexity and consciousness requires a very specific set of conditions that arise infrequently, but when they do arise, tend to produce results like the biosphere we inhabit. Whether that makes Earth designed or merely fortunate depends on how you interpret the relationship between probability and purpose. But either way, it makes our planet's suitability for life something worth contemplating with a sense of wonder and perhaps responsibility. When you peer into the internal architecture of Earth, not just its place in space, but its actual physical structure, you encounter systems that seem almost engineered for stability and function. Not perfectly engineered, nature doesn't work that way, but organized in ways that support long-term habitability through dynamic processes that regulate themselves. The planet's core consists of iron and nickel, arranged in 2 layers, a solid inner core, about 760 miles in radius, surrounded by a liquid outer core, roughly 1,400 miles thick. That liquid metal moves in complex patterns driven by Earth's rotation and heat flow from the interior. Those movements generate electric currents, which in turn create Earth's magnetic field, a planetary force field that deflects most solar wind and cosmic radiation. This geodynamo process isn't automatic. It requires precise conditions. The core has to contain enough iron and nickel to conduct electricity. The planet has to be large enough to retain the internal heat that keeps the outer core molten. The rotation has to be fast enough to stir the liquid metal, but not so fast as to disrupt the field generation. Earth happens to meet all these requirements and has done so for most of its 4.6 billion year history. Mars lost its magnetic field billions of years ago, probably because it's smaller than Earth and cooled more quickly. Venus rotates so slowly that it can't maintain a strong magnetic field even though it's nearly Earth's size. Among the rocky planets in our solar system, only Earth has retained robust magnetic protection throughout the age when life was developing. That protection matters more than you might think. Without it, Earth's atmosphere would gradually leak away into space, just as Mars's atmosphere apparently did. Solar wind would interact directly with the upper atmosphere, heating it until light gases like hydrogen and oxygen escape. Over geological time, the planet would dry out and become sterile. Above the core lies the mantle, about 1,800 miles of hot, slowly flowing rock that drives plate tectonics. The mantle isn't molten in the sense of liquid metal, but it's hot enough and under enough pressure to deform plastically over long time periods. It flows like taffy, very, very slowly. That flow creates convection patterns that bring hot material up from the deep interior and cycle cooler material back down. The upper boundary of the mantle interacts with Earth's thin crustal plates, pushing them apart at spreading centers, pulling them down at subduction zones, gradually recycling the surface of the planet. This constant, slow renovation isn't just geological housekeeping, it's a planetary thermostat. When atmospheric carbon dioxide levels rise, silicate rocks weather more rapidly, pulling CO2 out of the atmosphere. When they fall, volcanic activity releases stored carbon back into the air. The balance isn't precise. Climate can vary significantly over geological time, but it operates within bounds that keep the planet from freezing solid or boiling away. Plate tectonics also creates geographical diversity. Mountain ranges, ocean basins, island chains, continental margins, all shaped by the collision, separation, and sliding of crustal plates. That topographic complexity affects climate patterns, ocean circulation, the distribution of rainfall. It creates isolated environments where different evolutionary pathways can unfold, leading to the biological diversity we see today. The process requires a mantle with just the right viscosity, thick enough to flow but not so liquid that it can't maintain convection patterns. Too stiff, and nothing moves, the surface becomes geologically dead like Mars. Too fluid and plate boundaries become chaotic, the surface gets constantly reworked without developing stable continental masses. Earth's crust is thin compared to the rest of the planet, only about 5 miles thick under the oceans, 20–30 miles under continents, but it's where all surface life exists, and its composition is remarkably suited to biological needs. The continental crust contains high concentrations of elements that life requires: carbon, nitrogen, phosphorus, sulfur, calcium, potassium, trace metals. Those elements didn't all come from Earth's original accretion. Many were delivered later by comets and asteroids during the late heavy bombardment, a period about 4 billion years ago when the inner solar system experienced intense cratering. That bombardment could have been catastrophic for any emerging life, but it also brought water and organic compounds that Earth might otherwise have lacked. The timing seems fortuitous, early enough that the delivered materials could be incorporated into planetary development, but late enough that Earth had differentiated into core, mantle, and crust. The bombardment was heavy enough to deliver essential volatiles, but not so intense as to completely sterilize the surface or prevent atmospheric retention. Even today, Earth continues to receive material from space, but at a much reduced rate. Cosmic dust settles constantly. Occasional meteorites deliver samples of asteroids and other planets. Very rarely, large impacts create temporary disruptions, but also inject energy and materials that can drive evolutionary change. The distribution of elements in Earth's crust shows patterns that seem optimized for complexity. Carbon exists in forms that can create both stable storage limestone and dynamic cycling atmospheric CO2 organic compounds. Iron is abundant enough to support biological electron transport, but not so abundant as to create toxic conditions. The ratio of oxidizing to reducing compounds allows for diverse metabolic strategies. Water covers about 70% of Earth's surface, enough to moderate climate and support marine ecosystems, but not so much as to submerge all land. The distribution between oceans, lakes, rivers, groundwater, and atmospheric vapor creates a hydrological cycle that moves nutrients, moderates temperature, and maintains the chemical conditions that life depends on. The atmosphere itself consists of about 78% nitrogen, 21% oxygen, and trace amounts of other gases including carbon dioxide, water vapor, and noble gases. That composition isn't static, it's maintained by biological and geological processes working in concert. Plants and algae produce oxygen through photosynthesis. Animals consume oxygen through respiration. Volcanoes release gases from the interior. Weathering of rocks consumes atmospheric carbon dioxide. The balance isn't perfect, but it's remarkably stable considering how many processes could perturb it. Oxygen levels high enough to support complex metabolism, but not so high as to make combustion uncontrollable. carbon dioxide concentrations that maintain a modest greenhouse effect without runaway heating, water vapor that creates clouds and precipitation without overwhelming the system. Atmospheric pressure at sea level, about 14.7 pounds per square inch, allows liquid water to exist across a wide temperature range while supporting efficient gas exchange in biological systems. Too low and water would boil at body temperature. Too high and breathing would become difficult for air-breathing organisms. The atmosphere also provides protection from space debris. Small meteoroids burn up due to friction with air molecules, creating the shooting stars we occasionally see but preventing constant bombardment of the surface. Larger objects might penetrate the atmosphere, but they're slowed and often fragmented, reducing their impact energy. Ozone in the stratosphere absorbs most ultraviolet radiation from the sun, the wavelengths that damage DNA and other biological molecules. That ozone forms naturally through interactions between oxygen and solar radiation, creating a self-regulating shield that adjusts to changing conditions. Without it, life on land would be impossible. With too much, beneficial wavelengths might be blocked as well. All these systems, the magnetic field, plate tectonics, atmospheric composition, hydrological cycling, interact with each other in ways that maintain planetary habitability, not through conscious coordination, but through feedback mechanisms that tend to resist extreme departures from life-supporting conditions. When one system shifts, others respond in ways that often moderate the change. It's not perfect homeostasis. Earth's climate and surface conditions have varied significantly over geological time, but the variations have remained within bounds that allow life not just to survive but to diversify and complexify. From this perspective, Earth resembles a self-regulating system, not alive in the biological sense, but exhibiting properties we associate with living things: stability through dynamic response, resistance to perturbation, the ability to maintain organization in the face of constant change. Whether that represents design or emergence, intention or self-organization, depends on how you interpret the relationship between structure and function. But either way, it suggests that our planet's habitability isn't just a matter of being in the right place at the right time. It's also about being the right kind of system, one that maintains the conditions it needs to continue functioning. Hanging in the sky every night, sometimes bright, sometimes dim, always changing phase, the moon seems like Earth's natural companion, but when you examine its properties and effects more closely, you realize it's rather extraordinary. Not just because it's there, but because of how precisely its size, distance, and gravitational influence seem calibrated to support Earth's long-term stability. The moon is unusually large relative to its planet. At about 1/4 Earth's diameter, it's proportionally much bigger than most moons in the solar system. Mars has 2 tiny captured asteroids. The gas giants have numerous moons, but even their largest satellites are small fractions of the parent planet's size. Earth-Moon looks more like a double planet system than a typical planet-moon arrangement. How did this configuration arise? The leading scientific theory involves a catastrophic collision early in Earth's history. A Mars-sized object called Thelia apparently struck the young Earth at an angle, blasting enormous amounts of material into orbit. That debris eventually condensed into the moon, but the process required an incredibly specific set of circumstances. The impactor had to be just the right size, large enough to eject substantial material but not so large as to destroy Earth entirely. The collision angle had to be oblique rather than head-on, steep enough to transfer energy efficiently but not so steep as to simply merge the two bodies. The timing had to be appropriate, after Earth had differentiated into core and mantle but before the surface had cooled completely. Even if the collision went as theorized, the resulting debris disk had to evolve in ways that produced a single large moon rather than multiple small ones, or a ring system that eventually dissipated. The moon had to form at a distance that would remain stable over billions of years, close enough to have significant gravitational effects, but far enough away to avoid tidal disruption. And it has been slowly moving away from Earth ever since, as tidal friction gradually transfers angular momentum from Earth's rotation to the moon's orbit. Early in Earth's history, the moon was much closer, and Earth spun much faster. Days were only about 6 hours long, and tides were enormous. Over geological time, the system has evolved toward its current configuration where days are 24 hours long, and tidal ranges are substantial but not catastrophic. That evolution continues today. The moon recedes from Earth at about 1.5 inches per year, an imperceptible change on human timescales, but significant over geological time. Billions of years from now, the moon will be far enough away that it will no longer stabilize Earth's axial tilt or produce significant tides. But that's so far in the future that it doesn't affect the habitability that allowed complex life to evolve. The moon's most important function may be stabilizing Earth's rotation axis. Without it, gravitational perturbations from other planets would cause Earth's tilt to vary chaotically between nearly 0 degrees and more than 85 degrees over periods of tens of thousands of years. Sometimes the poles would point almost directly at the sun, creating extreme seasonal variations. Sometimes there would be no seasons at all. That kind of climate chaos would make it difficult for ecosystems to adapt and persist. Species evolved to specific temperature, and seasonal patterns would face constant, unpredictable changes in their environment. Complex food webs might collapse and reform repeatedly. The stable climate zones that allow forests, grasslands, and other major biomes to develop might never establish themselves. With the moon's stabilizing influence, Earth's axial tilt varies only between about 22 and 25 degrees over a 41,000 year cycle. Enough variation to drive ice age cycles, but not enough to cause complete climate reorganization. That stability has persisted throughout the period when multicellular life was developing, allowing ecosystems time to establish and diversify. The moon also drives Earth's tides, and those tides have probably played important roles in both the origin and ongoing evolution of life. The rhythmic exposure and flooding of coastal areas creates unique environments where marine and terrestrial conditions alternate. Early in Earth's history, such tidal zones might have provided the concentration and mixing effects that helped complex organic molecules form and interact. Even today, tidal ecosystems are among the most productive on Earth. Estuaries, salt marshes, mangrove swamps, rocky intertidal zones all depend on the regular cycling between submersion and exposure that tides provide. Many species time their reproduction, feeding, and migration to tidal rhythms. The moon's gravitational pull connects terrestrial and marine environments in ways that enhance biological diversity. Tides also affect the solid Earth itself. The planet's crust rises and falls by several inches as the moon's gravity creates bulges that move around Earth with the tidal cycle. That flexing may help drive geological processes, adding energy to tectonic activity, affecting patterns of earthquake occurrence, influencing the circulation of groundwater. Beyond its gravitational effects, the moon provides light that many organisms use for navigation, timing, and behavior. Coral reefs spawn in synchronization with lunar cycles. Many animals are more active during bright moonlit nights. Predator-prey relationships shift with changing lunar phases. The moon has become integrated into the biological rhythms of Earth's biosphere. The moon also affects human culture in ways that connect astronomy with meaning. Lunar calendars, agricultural timing, religious observances, poetry, art. The moon's phases have provided a celestial clock that helped early civilizations track time and season. Its regular changes make it an obvious symbol for cycles, renewal, the passage of time. From a design perspective, the moon's properties seem almost too convenient. It's large enough to significantly affect Earth's rotation and create substantial tides, but not so large as to lock Earth into synchronous rotation or cause catastrophic tidal forces. It's at the right distance to stabilize axial tilt without dominating Earth's dynamics. It provides enough light to be useful for biological timing without being bright enough to disrupt circadian rhythms. The fact that the moon appears almost exactly the same size as the sun in Earth's sky, allowing for total solar eclipses where the moon precisely covers the solar disk, is certainly coincidental. But it's a remarkable coincidence that has allowed humans to study the sun's corona, make crucial discoveries about solar physics, and experience one of nature's most awe-inspiring phenomena. If you wanted to design a planetary system optimized for the development of complex life, you might well include a large satellite like Earth's moon. It would stabilize climate, create tidal environments, provide celestial timing, and add gravitational complexity that enriches the system's dynamics. The fact that Earth happens to have such a satellite, and that it apparently formed through an extremely unlikely series of early collisions, raises questions about how probable or improbable our particular configuration really is. Other planets in our solar system lack comparable moons. Mars's satellites are tiny. Venus and Mercury have none at all. The gas giants have many moons, but they orbit in environments too hostile for surface life. Among rocky planets in the habitable zone, Earth's moon appears to be unique and uniquely beneficial. Whether that represents design, chance, or some combination of both, it's another factor that makes Earth's habitability seem less inevitable and more remarkable than it might initially appear. Of all the forces shaping our daily experience, gravity might be the most invisible and the most essential. We don't notice it unless something falls, but it's constantly working to hold everything together. Not just objects on Earth's surface, but the planet itself, the solar system, the galaxy. Gravity is the invisible architecture that makes structure possible in a universe that would otherwise fly apart. Gravity is actually a weak force compared to electromagnetism or the nuclear forces that hold atoms together. A small magnet can lift a paperclip against the gravitational pull of the entire Earth. But what gravity lacks in strength, it makes up for in universality and persistence. It never turns off, never gets blocked, and acts on everything that has mass or energy. That quiet persistence makes gravity the universe's primary organizer. Without it, the matter that formed Earth would still be dispersed in a thin cloud, never collapsing into anything dense enough to support the complex chemistry that life requires. Planets exist because gravity pulled together dust and gas over millions of years, compacting it until pressure and heat transformed loose material into solid worlds. Earth's internal structure reflects gravity's organizing influence. Dense materials like iron and nickel sank toward the center during the planet's formation, while lighter elements rose toward the surface. That gravitational differentiation created the layered structure, iron core, rocky mantle, thin crust, that drives geological processes and generates the magnetic field that protects us from space radiation. Gravity also maintains Earth's orbit around the Sun, a delicate balance between the planet's forward momentum and the Sun's gravitational pull. Too fast and Earth would escape into interstellar space, too slow and it would spiral inward. The orbital speed, about 67,000 miles per hour, keeps us falling around the Sun in a stable ellipse that has persisted for billions of years. That orbital stability provides the consistent energy input that makes long-term climate patterns possible. Earth receives roughly the same amount of solar radiation year after year, with only small variations due to orbital eccentricity and solar activity. Without that consistency, life would face constant energy fluctuations that might prevent the establishment of stable ecosystems. The Moon's orbit around Earth represents another gravitational relationship that has shaped our planet's habitability. The Moon's gravity creates tides in both the oceans and the solid Earth, effects that have influenced everything from coastal evolution to the length of our days. Tidal friction has gradually slowed Earth's rotation from the rapid spin of early planetary formation to the 24-hour cycle that most life has adapted to. Gravity affects biological processes more directly than we usually realize. Our bones grow dense enough to support our weight against gravitational pull. Our cardiovascular systems pump blood upward against gravity's downward tug. Our inner ears detect gravitational orientation to help maintain balance. Even plants respond to gravity. Roots growing down, stems growing up, guided by cellular mechanisms that sense which way is down. In low-gravity environments, these biological systems don't work properly. Astronauts experience bone loss, muscle atrophy, fluid redistribution, changes in cardiovascular function. Their bodies are adapted to Earth's specific gravitational field, 9.8 meters per second squared. Change that value significantly and human physiology would need to be very different. If Earth were more massive, gravity would be stronger. Bodies would need to be more robust to function, probably shorter and stockier. Atmospheric pressure would be higher, weather systems more intense. If Earth were less massive, gravity would be weaker. The atmosphere might be thinner, possibly unstable over geological time. Liquid water might behave differently. Flight would be easier, but retaining an atmosphere would be harder. The strength of Earth's gravity reflects the planet's mass, which in turn reflects how much material was available during planetary formation and how efficiently it was gathered together. Too little mass and you get Mars, too small to retain a thick atmosphere or strong magnetic field. Too much mass, and you might get a gas giant unsuitable for surface life, or a super-Earth with crushing surface gravity. Gravity also shapes larger-scale structure in ways that affect habitability. Jupiter's massive gravitational field acts as a cosmic vacuum cleaner, capturing or deflecting comets and asteroids that might otherwise impact Earth. The gas giant's position and mass help maintain stable orbits throughout the solar system, preventing chaotic interactions that could disrupt planetary development. On even larger scales, gravity assembles galaxies and determines their structure. The Milky Way's gravitational field keeps our solar system in a relatively stable orbit, not too close to the chaotic galactic center, not so far out that heavy elements would be scarce. The galaxy's spiral arms, driven by gravitational waves, may periodically expose the solar system to increased radiation or cosmic debris, but those exposures appear to be manageable rather than catastrophic. Gravity curves space-time itself, a prediction of Einstein's general relativity that has been confirmed through astronomical observations. That curvature affects the paths of light rays, the rate of time's passage, even the expansion of the universe. We live embedded in gravitational fields that shape not just the motion of matter, but the fabric of reality itself. The cosmological constant, the energy density of empty space that drives cosmic expansion, has a value that allows for the formation of structure on scales from stars to galaxy clusters. If it were much larger, expansion would be so rapid that gravity couldn't pull matter together to form galaxies and stars. If it were much smaller or negative, the universe might collapse before star formation could occur. Even the strength of gravity itself, determined by what physicists call Newton's gravitational constant, appears to be finely tuned for the existence of stable stars and planets. Stronger gravity would make stars burn out too quickly. Weaker gravity might prevent star formation altogether or make planetary orbits unstable. These observations don't prove that gravity was designed to support life, but they do suggest that small changes in gravitational physics would make the universe much less hospitable to complexity and consciousness. Whether that's a profound coincidence or evidence of deeper organizational principles remains an open question. What's clear is that gravity provides the scaffolding on which everything else is built, from the formation of atoms in stellar cores to the evolution of life on planetary surfaces. From the structure of DNA to the dynamics of ecosystems, everything depends on gravity's patient, persistent, universal influence. It's a force that connects the smallest scales to the largest, the quantum fluctuations that seeded cosmic structure to the galactic motions we observe today. In a universe where so much seems chaotic and unpredictable, gravity provides reliable order, not rigid control, but consistent relationships that make complexity possible. And we rarely think about it until something falls and reminds us that even invisible forces still govern our daily experience. Of all the substances on Earth, Water might seem the most ordinary, hydrogen and oxygen, two of the universe's most common elements, combined in the simplest possible ratio. But when you examine how water behaves and what it makes possible, it becomes clear that this humble molecule is anything but ordinary. Its properties are so perfectly suited to supporting life that it's hard to imagine biology working without it. Water exists in all three states: solid, liquid, and gas, within the narrow temperature range that Earth experiences naturally. That's unusual. Most substances favor one state under typical planetary conditions, but water can freeze, melt, evaporate, and condense as climate varies seasonally and geographically. Those phase changes don't just passively respond to temperature, they actively regulate it. When water evaporates, it absorbs large amounts of energy, cooling the surface it leaves behind. When it condenses into clouds, it releases that energy, warming the atmosphere. This process moves heat from equatorial regions toward the poles, from oceans to continents, from summer to winter. It's a planetary air conditioning system that moderates temperature extremes and makes large areas of Earth habitable. Water also has an unusually high specific heat, meaning it can absorb and release large amounts of thermal energy without dramatic temperature changes. Oceans and large lakes act as thermal buffers, storing heat during warm periods and releasing it during cool periods. Coastal regions have more moderate climates than continental interiors, partly because nearby water bodies smooth out temperature variations. Perhaps most remarkably, water expands when it freezes. Most substances become denser as they cool, but water reaches maximum density at about 4 degrees Celsius and then becomes less dense as it approaches freezing. This means ice floats, and that seemingly minor fact has enormous consequences for life on Earth. When lakes and oceans freeze, they do so from the top down. The ice forms an insulating layer that protects liquid water underneath, allowing aquatic life to survive winter, even in regions where surface temperatures drop well below freezing. If ice were denser than liquid water, it would sink as it formed. Water bodies would freeze from bottom to top, potentially becoming solid ice blocks that would take much longer to thaw. The floating ice also reflects sunlight, helping prevent complete thawing during brief warm periods and stabilizing ice age cycles. Without this property, Earth's climate might oscillate more wildly between frozen and ice-free states. Water is often called the universal solvent because it can dissolve more substances than almost any other liquid. This happens because water molecules are polar, they have a slightly positive end and a slightly negative end, which allows them to surround and separate ions and other charged particles. In biological systems, this property is essential for transporting nutrients, removing wastes, and enabling the chemical reactions that sustain life. Blood, sap, cellular fluids, all depend on water's ability to carry dissolved substances from where they're produced to where they're needed. Without an effective solvent, complex organisms couldn't maintain the internal chemistry that multicellular life requires. Water's polarity also enables hydrogen bonding, weak attractions between water molecules that give liquid water many of its unique characteristics. These bonds make water more cohesive than you'd expect from such a small molecule. That cohesion allows water to move through plant tissues from roots to leaves, sometimes rising hundreds of feet against gravity in tall trees. Surface tension, another result of hydrogen bonding, creates the interface effects that many small organisms depend on. Water striders walk on water's surface. Capillary action moves water through soil and narrow spaces. The meniscus in a glass demonstrates how water's cohesive properties interact with other materials. In biological systems, hydrogen bonding helps stabilize the three-dimensional shapes of proteins and nucleic acids. DNA's double helix is held together partly by hydrogen bonds between base pairs. Protein folding depends on hydrogen bonding between different parts of the molecular chain. Water isn't just the medium in which these processes occur, it's an active participant in maintaining biological structure. Water's transparency in visible light allows photosynthesis to occur not just at the surface of oceans and lakes, but at considerable depths. Sunlight can penetrate dozens or even hundreds of feet into clear water, supporting plant and algae growth that forms the base of aquatic food webs. If water were opaque, underwater ecosystems would be limited to the narrow surface zone or would have to depend entirely on chemosynthesis rather than photosynthesis. The temperature at which water boils and freezes depends on atmospheric pressure, and those transition points happen to bracket the range of temperatures that exist naturally on Earth's surface. At sea level, water remains liquid between 0 and 100 degrees Celsius, a 100-degree window that encompasses most of the temperature variation that life experiences. Change Earth's atmospheric pressure significantly, and water would either boil away or freeze solid under conditions that are otherwise habitable. The relationship between atmospheric pressure and water's phase transitions appears to be precisely calibrated for maintaining liquid water across most of Earth's surface, most of the time. Water also has unusual behavior when it comes to density and circulation. Cold water is denser than warm water, except near freezing, where the expansion effect dominates. This creates circulation patterns in oceans and lakes where water masses of different temperatures move in predictable ways, mixing nutrients and oxygen, distributing heat, and creating the currents that affect regional climates. The global water cycle, evaporation, cloud formation, precipitation, runoff, redistributes fresh water from oceans to land, making terrestrial life possible. This cycle is driven by solar energy, but depends critically on water's specific properties. The amount of energy required for evaporation, the conditions that trigger condensation, the size and behavior of water droplets, all influence how effectively the cycle transports water from sea to land. Even the molecular structure of water, two hydrogen atoms bonded to oxygen at an angle of 104.5 degrees, seems optimally designed for its biological roles. Change that angle slightly, and water's properties change dramatically. Its solvent capabilities, its hydrogen bonding behavior, its thermal characteristics, all depend on that specific geometry. Why should the fundamental physics and chemistry of matter yield a molecule so perfectly suited for supporting complex chemistry and biology? Water's properties aren't accidental. They emerge from the quantum mechanical rules that govern how atoms interact. But those rules themselves could have been different, and in most possible universes they probably are. The fact that our universe's physical laws produce a substance with water's remarkable collection of life-supporting properties, and that this substance is abundant throughout the cosmos, suggests either extraordinary fortune or underlying principles favor the emergence of complexity. Water is common in the universe. Hydrogen is the most abundant element. Oxygen is produced in stellar cores and distributed through space when stars explode. But having liquid water in large, stable quantities on a planetary surface, that's much rarer. It requires the right temperature, the right atmospheric pressure, the right geological activity to maintain the hydrological cycle. Earth has maintained vast liquid oceans for billions of years, and those oceans have remained liquid through ice ages, asteroid impacts, volcanic episodes, and other disruptions that could have boiled them away or frozen them solid. That stability has provided the aquatic environment where life likely originated, and the climate regulation that has kept conditions suitable for life's subsequent evolution and diversification. Whether water's remarkable suitability for life represents design or discovery, intention or emergence, it's certainly one of the most striking examples of how the basic building blocks of reality seem fine-tuned for supporting the complex chemistry that makes consciousness possible. When you start paying attention to the shapes that life takes, the way trees branch, leaves spiral, shells curve, crystals grow, you begin to notice that certain patterns appear again and again across vastly different scales and contexts. It's not just superficial resemblance, it's deep structural similarity, as if all of nature follows the same underlying grammar of form. Symmetry is perhaps the most obvious of these patterns. Bilateral symmetry in animals, where left and right sides mirror each other. Radial symmetry in flowers and sea creatures, where parts radiate outward from a central point. Rotational symmetry in crystals and cells, where structures look identical after rotation by specific angles. These symmetries aren't merely decorative, they often serve functional purposes. Bilateral symmetry helps animals move efficiently and process sensory information. Radial symmetry allows organisms to interact with their environment from all directions. Crystalline symmetry reflects the most stable arrangements of atoms and molecules. But functionality doesn't fully explain our response to symmetry. Humans are strongly attracted to symmetrical forms in faces, architecture, art, music. We seem to be hardwired to find symmetry beautiful, meaningful. That preference might have evolutionary origins. Symmetrical features often indicate health and genetic quality, but it extends far beyond mate selection to encompass our entire aesthetic sensibility. Why should mathematical regularity be so appealing to minds that evolved to find food and avoid predators? Why does our sense of beauty align so closely with the geometric principles that govern both natural forms and human creations? Spiral patterns offer another example of deep structural consistency. You see spirals in galaxies, hurricanes, whirlpools, nautilus shells, pine cones, sunflower seed heads, DNA molecules, even the cochlea of the inner ear. These aren't superficial similarities. They represent similar solutions to similar problems across radically different contexts. Many of these spirals follow mathematical patterns related to the Fibonacci sequence, a series where each number is the sum of the two preceding ones, 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. The ratio between consecutive Fibonacci numbers approaches what's called the golden ratio, approximately 1.618, a proportion that appears throughout nature and human art. Why should the same mathematical relationship govern the arrangement of petals in a flower and the structure of spiral galaxies? Why do growth patterns in biological systems so often converge on ratios that we find aesthetically pleasing? Fractal patterns provide yet another example of nature's geometric consistency. Fractals are structures that look similar at different scales. Zoom in on a piece, and it resembles the whole structure. Tree branches divide into smaller branches that divide into twigs that divide into smaller twigs. River networks split into tributaries that split into streams that split into rivulets. Lightning bolts fork into smaller channels that fork into still smaller ones. Blood vessels, lung airways, neural networks, all show fractal organization. It's an efficient way to distribute resources throughout a volume while minimizing the material needed for the distribution network. But it's also an aesthetic principle that shows up in art, architecture, and music across cultures. Hexagonal patterns appear wherever efficiency matters. Honeycombs, basalt columns, drying mud, soap bubbles, crystal structures all favor hexagonal arrangements because they provide maximum space with minimum material or energy. The hexagon is mathematically optimal for many packing and tiling problems. But hexagons also appear in contexts where efficiency isn't obviously the driving factor, in artwork, decorative patterns, architectural elements. The form seems to appeal to something deeper than practical optimization. Even the way organic shapes grow often follows mathematical rules. The logarithmic spiral of a nautilus shell reflects the need to maintain constant proportions while adding new material. The branching angles of trees optimize light capture while maintaining structural integrity. The shapes of leaves balance surface area for photosynthesis against volume for structural support. These aren't random solutions that happen to work. They're convergent evolution toward mathematical principles that govern how space, energy, and materials can be organized most effectively. The same principles show up independently in biological systems, geological processes, and human designs. Crystal formation reveals how matter itself organizes according to geometric principles. Atoms arrange themselves in repeating patterns that minimize energy while maintaining stability. The resulting shapes, cubes, octahedra, dodecahedra, complex polyhedra emerge spontaneously from the internal logic of molecular structure, but those same geometric forms appear in biological systems, architectural designs, and artistic creations. The Platonic solids, the five regular polyhedra that fascinated ancient Greek mathematicians, can be found in virus structures, radiolarians, geodesic domes, and decorative art. What's particularly striking is how often these patterns emerge from simple rules applied repeatedly. Fibonacci spirals result from optimizing packing while maintaining proportional growth. Fractal branching emerges from recursive division following efficiency constraints. Hexagonal tilings arise from minimizing perimeter for a given area. Complex, beautiful, functionally effective structures emerge from surprisingly simple underlying principles that suggests there might be deep mathematical laws that govern not just human thought and creativity, but the way matter and energy organize themselves throughout the universe. The mathematician Eugene Winger wrote about the unreasonable effectiveness of mathematics in the natural sciences. Why should mathematical concepts developed through pure abstract reasoning turn out to describe physical reality so precisely? Why should the universe be comprehensible to mathematical minds? Perhaps because both mathematics and physical reality operate according to the same underlying principles that favor certain kinds of organization, certain relationships between parts and wholes, certain solutions to the problems of existing in space and time. This could suggest that what we call sacred geometry isn't mysticism. It's recognition of actual structural principles that govern reality at every scale. The spiral of a galaxy and the spiral of a DNA molecule might follow the same pattern not by coincidence, but because both are solutions to similar organizational challenges within the same mathematical universe. From this perspective, the appearance of design in nature might reflect not conscious intention, let's call it mathematical intention, the tendency of matter and energy to organize themselves according to principles that favor stability, efficiency, beauty, because those principles are built into the fabric of reality itself. When we peer into the molecular machinery of life, the cellular systems that sustain every living thing, we encounter levels of organization and precision that challenge our ordinary categories of understanding. These aren't just chemical reactions happening in biological soup. They're coordinated processes that store, transmit, and execute information with a sophistication that rivals anything humans have engineered. At the heart of it all is DNA, deoxyribonucleic acid, the molecule that carries genetic information in every known form of life. But calling it a molecule undersells what it actually is. DNA is a code written in a four-letter chemical alphabet that specifies the structure and function of every protein an organism needs to build and maintain itself. The comparison to human languages isn't metaphorical. DNA has syntax, rules about how genetic information is structured. It has grammar, conventions that determine meaning. It has redundancy, multiple codons can specify the same amino acid, providing error tolerance. It has punctuation, start and stop signals that mark the boundaries of genes. Most remarkably, DNA contains not just data but instructions for reading that data. The genetic code includes sequences that regulate when and where genes are expressed, how much protein to produce, what environmental conditions should trigger changes in gene activity. It's self-modifying code, a program that can rewrite itself in response to changing circumstances. Every cell in your body contains the complete genetic instructions for building an entire human being, but only a fraction of those instructions are active at any given time. Liver cells express genes for liver function while suppressing genes for brain function. Muscle cells do the reverse. The same code produces radically different outcomes depending on which parts are activated. This regulatory complexity allows a single genome to specify organisms of extraordinary diversity and sophistication. The human genetic code contains roughly 3 billion base pairs, enough information to fill a library of thousands of books. But it's not just the quantity of information that's impressive, it's the quality of its organization. Genes aren't randomly scattered throughout the genome. They're arranged in functional clusters with related genes often located near each other. Regulatory sequences are positioned precisely where they can influence the genes they control. The three-dimensional structure of DNA within the cell nucleus creates additional layers of organization that affect gene expression. Even the way genetic information is packaged shows remarkable efficiency. DNA molecules are incredibly long. If you stretched out all the DNA in a single human cell, it would reach about 6 feet, yet it's packed into a nucleus just a few thousandths of an inch across. This requires elaborate folding and organizing systems that make the information accessible when needed, while keeping it compact and protected. The process by which genetic information becomes functional proteins involves multiple steps, each requiring precise molecular machinery. DNA is transcribed into RNA by enzymes that recognize specific starting points and copy exactly the right sequences. That RNA is then processed, sections called introns are removed. The remaining pieces are spliced together. The processed RNA travels to ribosomes, molecular machines that read the genetic code 3 letters at a time and assemble amino acids in the correct order to build proteins. Those proteins then fold into complex three-dimensional shapes that determine their function. Some become enzymes that catalyze chemical reactions. Others become structural components. Still others become regulatory molecules that control gene expression. The folding process itself is remarkable. A protein might consist of hundreds of amino acids that must arrange themselves into exactly the right configuration to function properly. There are astronomical numbers of possible arrangements, but somehow proteins find their correct shapes reliably and quickly. They're assisted by other proteins called chaperones that help guide the folding process, molecular assistants that ensure quality control. All of this happens continuously in every cell. Thousands of genes being transcribed, thousands of proteins being synthesized, folded, modified, transported to where they're needed. The cell manages these processes through elaborate networks of signals and feedback loops that coordinate activity across all its molecular systems. What's particularly striking is how error-prone this process could be, and how rarely serious errors actually occur. DNA replication involves copying billions of base pairs with extraordinary accuracy. Transcription and translation must proceed without dropping or misreading genetic information. Protein folding must achieve precise shapes despite thermal motion that's constantly trying to disrupt molecular structure. Yet the error rates are remarkably low. DNA replication has built-in proofreading mechanisms that catch and correct most mistakes. Transcriptional errors are minimized by quality control systems. Misfolded proteins are recognized and recycled before they can cause problems. The cell doesn't just execute genetic programs, it responds to its environment and modifies those programs accordingly. When nutrients are scarce, genes for metabolic efficiency are upregulated. When the cell is damaged, repair systems are activated. When external signals indicate the need for cell division, growth-related genes are expressed. This isn't simple stimulus-response behavior. It's information processing that integrates multiple inputs, evaluates current conditions, and implements appropriate responses. The cell exhibits something that looks remarkably like intelligence, not consciousness, but purposeful behavior, based on information gathering and decision-making. Consider the immune system, a network of cells and molecules that can distinguish between self and non-self. Remember previous encounters with threats, and mount increasingly effective responses to repeated challenges. Immune cells rearrange their own DNA to create novel antibodies, essentially rewriting their genetic code to address specific threats. The immune system learns, it gets better at recognizing and responding to pathogens it has encountered before. It generalizes. Antibodies that recognize one variant of a virus often provide some protection against related variants. It maintains memory. Immune cells can remain dormant for decades and then rapidly reactivate when they encounter familiar threats. Or consider development. the process by which a fertilized egg becomes a complex multicellular organism. This involves precise timing of gene expression, coordinated cell movements, formation of tissues and organs, establishment of body plans. Cells differentiate into hundreds of specialized types, each expressing different subsets of the genome. The embryo doesn't just grow, it constructs itself according to a developmental program encoded in its genes, but executed through dynamic interactions between cells. Chemical signals guide cell migration. Physical forces shape growing tissues. Feedback loops ensure that organs develop in the right proportions and connections. This process is so complex that scientists are still working to understand it fully, yet it unfolds reliably in every normally developing organism. The same genome that produces a human brain also produces human kidneys, human bones, human skin, each with entirely different cellular architecture and biochemistry. Even basic cellular processes show this same combination of complexity and reliability. Cellular respiration, the process that extracts energy from nutrients, involves dozens of enzymes working in precisely coordinated sequences. Photosynthesis captures solar energy and converts it into chemical forms that can power biological processes. These are sophisticated biochemical systems that operate with efficiency that human technology struggles to match. When you step back and consider the overall picture, genetic code that stores and executes information, regulatory networks that control gene expression, molecular machines that synthesize and transport proteins, quality control systems that maintain accuracy, repair mechanisms that fix damage, developmental programs that build complex organisms from single cells, it becomes difficult to see this as the product of undirected chemical processes alone. This doesn't necessarily imply conscious design, but it does suggest systematic organization toward functional outcomes. The molecular machinery of life exhibits properties we usually associate with engineered systems: modularity, redundancy, error correction, adaptive control, hierarchical organization. Whether this represents the discovery of engineering principles through evolutionary processes or the implementation of engineering principles through some form of natural design, it's certainly one of the most sophisticated information processing and control systems we know of, and it operates in every cell of every living thing, maintaining the conditions that make consciousness and contemplation possible. The idea that biological systems operate according to some form of programming language isn't just metaphor. It's become a literal framework for understanding and manipulating life. Scientists now routinely edit genetic code, design synthetic biological circuits, engineer organisms with novel functions. We've learned to read and write in the language of DNA. But we didn't invent that language. We discovered it already operating, already functional, already maintaining the conditions for our own existence. The question of where that language came from, how it achieved such sophistication, whether it represents intention or emergence, remains as compelling now as ever. When you think about DNA and genetic codes, cellular machinery and biological information processing, it's natural to make comparisons with human technology. But lately, those comparisons have become more than analogies. As our digital systems grow more sophisticated, they're starting to exhibit properties that look remarkably biological, and that convergence raises intriguing questions about the relationship between designed and evolved systems. Early computers were built like machines, rigid components, fixed programs, predictable behaviors. But modern artificial intelligence operates differently. Neural networks learn from experience. Algorithms evolve through selection and variation. Complex behaviors emerge from simple rules applied repeatedly across interconnected systems. We now routinely evolve software rather than programming it directly. Genetic algorithms generate solutions to problems by creating populations of potential answers, selecting the best performers, and breeding new generations with modifications. Machine learning systems discover patterns in data that their programmers never explicitly taught them to recognize. Some of the most powerful AI systems are ones we don't fully understand. We can observe their inputs and outputs, but the internal processes that transform one into the other operate through networks too complex for human comprehension. They work often better than systems we designed step by step, but they achieve their results through methods that resemble biological intelligence more than traditional programming. This convergence between evolved and designed intelligence has led to speculation about the nature of intelligence itself. If both biological brains and artificial neural networks can exhibit learning, adaptation, pattern recognition, even creativity, perhaps intelligence isn't tied to any particular substrate. Perhaps it's an emergent property of sufficiently complex information processing systems, regardless of whether they're made of neurons or silicon. That possibility has given new relevance to an old philosophical question, the simulation hypothesis. If artificial systems can achieve intelligence, consciousness, even self-awareness, could we ourselves be artificial? Could the reality we experience be a simulation running on some unimaginably powerful computational substrate? The idea isn't science fiction anymore. It's a serious hypothesis discussed by physicists, computer scientists, and philosophers. If a civilization advanced far enough to simulate conscious beings, the argument goes they might create many such simulations. Statistically, there would be more simulated conscious beings than naturally occurring ones, making it more likely that any given conscious being is simulated rather than original. We have no direct evidence for this possibility, but there are intriguing hints. Physical reality exhibits properties that look suspiciously computational. Space and time appear to be quantized, divided into discrete units rather than continuous. Information seems to be fundamental. Some physicists argue that matter and energy are emergent properties of information processing, rather than the other way around. Quantum mechanics describes reality in terms that sound remarkably like computational processes. Quantum states exist in superposition until observed, like variables that have no definite value until a program queries them. Quantum entanglement creates correlations that persist across arbitrary distances, like shared memory in a distributed computing system. Even if we're not living in a simulation, the fact that reality can be modeled computationally with extraordinary precision suggests deep connections between physical and informational processes. The same mathematical principles that govern digital systems also govern natural phenomena, which could reflect either the computational nature of reality or the reality-based nature of computation. This blurring of boundaries between natural and artificial extends beyond intelligence to entire ecosystems. We now simulate evolution itself, creating digital organisms that reproduce, mutate, compete for resources, and adapt to changing environments. These artificial life forms evolve novel strategies that their programmers never anticipated. They develop cooperation, competition, predator-prey relationships, even primitive forms of communication. Virtual ecosystems can be remarkably lifelike, not in appearance, but in behavior. They exhibit the same population dynamics, resource cycles, evolutionary pressures, and emergent complexity that characterize biological ecosystems. The distinction between real and simulated life becomes less clear when the simulated organisms exhibit all the behaviors we associate with living systems. Some scientists have proposed that reality itself might be computational, that the universe operates like a vast information processing system, with physical laws as programming languages and quantum interactions as computational operations. In this view, matter and energy are how information manifests itself in space and time. If that's true, then the designed versus evolved distinction loses much of its meaning. Both natural evolution and artificial design would be types of information processing, different algorithms running on the same computational substrate. The appearance of design in nature might reflect the computational nature of reality itself, not conscious intention, but systematic organization according to informational principles. This perspective also suggests new ways of thinking about consciousness and identity. If our brains are biological computers, and if artificial computers can achieve consciousness, then consciousness might be transferable between substrates. We might be patterns of information processing that could in principle operate on different types of hardware. That possibility raises profound questions about the nature of existence, identity, mortality. If consciousness is informational rather than material, then death might be more like a computer shutting down than a fundamental termination. The pattern might be preserved, transferred, even backed up and restored. But these are speculations that push against the boundaries of current knowledge. What's certain is that the relationship between natural and artificial systems is becoming increasingly complex and intertwined. We create technologies that mimic biological processes. Biology exhibits properties that resemble designed systems. The boundaries between evolved and engineered intelligence continue to blur. Whether this convergence reveals deep truths about the nature of reality, or simply reflects the fact that intelligence tends towards similar solutions regardless of its origins, it's one of the most fascinating developments in our understanding of mind, matter, and the relationship between them. And it adds another dimension to the question we've been exploring. If Earth shows signs of design, and if the distinction between designed and evolved systems is becoming increasingly meaningless in our technological age, perhaps the question isn't whether our world was designed, but whether design and evolution are different words for the same underlying process of information, organizing itself into patterns that support complexity, intelligence, and ultimately consciousness capable of reflecting on its own existence. The simulation hypothesis doesn't require us to believe we're artificial, but it does invite us to consider whether the categories of natural and artificial, evolved and designed, might be human constructs that don't fully capture the nature of reality. Perhaps what matters isn't the origin of our existence, but the fact of it, and our ability to contemplate the remarkable systems that sustain us, whether they emerged through biological evolution, computational simulation, or something else entirely. When we ask whether Earth was designed, we often think in terms of conscious intention, a deliberate plan executed by an intelligent agent. But there's another way to approach the question, through the lens of emergent properties and self-organization. Complex systems, whether biological, computational, or physical, often exhibit behaviors and properties that weren't explicitly programmed or intended. They arise spontaneously from the interactions of simpler components following basic rules. Consider a flock of birds wheeling across the sky in perfect coordination. No bird is directing the others. No central intelligence is orchestrating their movements. Yet the flock moves as a unified entity, changing direction instantly, avoiding obstacles, maintaining cohesion. This behavior emerges from simple rules each bird follows. Stay close to nearby birds, avoid collisions, match the average direction of neighbors. Individual birds following these local rules create global patterns that look designed, and in a sense they are. Not designed by any conscious agent, but designed by the rules themselves and the way they interact across many individuals. The design emerges from the system rather than being imposed upon it. Earth's biosphere exhibits similar emergent properties at every scale. Ecosystems self-organize into stable configurations of producers, consumers, and decomposers. Chemical cycles regulate atmospheric composition without central control. Climate patterns emerge from the interactions of atmospheric, oceanic, and geological processes. The planet maintains habitability through countless feedback loops that resist perturbation and promote stability. None of this requires conscious oversight, yet the outcomes often look as if they were planned. The global carbon cycle keeps atmospheric CO2 within ranges that support life. Ocean currents distribute heat in ways that moderate regional climates. Biodiversity creates redundancy that makes ecosystems resilient to disruption. These aren't lucky accidents. They're emergent properties of how complex systems behave when their components interact over time. Negative feedback loops create stability. Positive feedback loops drive change and growth. Non-linear interactions produce unexpected outcomes that can be either beneficial or catastrophic. The key insight is that emergence can produce design-like outcomes without requiring a designer. Complex systems discover solutions to organizational problems through processes that look remarkably like intelligence, but operate through mechanism rather than intention. Evolution itself is perhaps the best example of this phenomenon. Random mutations combined with natural selection produce organisms of extraordinary sophistication and apparent design. No intelligence guides the process, yet it consistently moves toward greater complexity, efficiency, and adaptation to environmental challenges. But evolution doesn't just shape individual organisms, it shapes entire ecosystems, biogeochemical cycles, even planetary scale processes. The development of photosynthesis changed Earth's atmosphere and climate. The emergence of multicellular life altered ocean chemistry. Human intelligence is now affecting global systems in ways that will influence the planet's future evolution. From this perspective, asking whether Earth was designed becomes a question about the nature of emergence itself. Do complex systems naturally tend toward organization and stability? Are there built-in biases in the way matter and energy interact that favor the development of life-supporting conditions? Some scientists have proposed that complexity itself might be a fundamental feature of reality, that the universe naturally evolves towards states of greater organization and information processing capacity. This wouldn't require conscious intention, but it would mean that the emergence of life and intelligence isn't purely accidental. Others suggest that we're seeing selection effects, that we observe fine-tuned conditions, because only universes with such conditions produce observers capable of noticing them. In this view, apparent design is an inevitable consequence of the fact that observers can only exist in observable universes. But there's a third possibility, that the distinction between designed and emergent systems isn't as clear as we usually assume. Perhaps all design is emergence, the result of intelligent agents discovering solutions through processes that combine intention with exploration, planning with adaptation, conscious choice with unconscious selection. Human design rarely proceeds through pure rational planning. Engineers try different approaches, test prototypes, iterate based on feedback. Artists experiment with forms and materials, following intuitions that lead to unexpected discoveries. Even conscious design involves emergent processes where final outcomes aren't fully predictable from initial intentions. Similarly, biological evolution might involve processes that look more intentional than pure randomness suggests. Organisms actively modify their environments in ways that affect their own evolution. Epigenetic inheritance allows acquired characteristics to influence offspring. Symbiosis creates partnerships that drive rapid evolutionary change. The boundary between designed and evolved systems becomes even blurrier when we consider that human intelligence itself is a product of biological evolution. Our capacity for design, planning, and intentional creation emerge through natural processes. We are the universe becoming conscious of itself and using that consciousness to shape its further development. From this perspective, human technology and artificial intelligence represent new phases in the same evolutionary process that produced biological complexity. We're not separate from nature, we're nature becoming aware of its own patterns and learning to direct its own evolution. This doesn't resolve the question of whether Earth was designed, but it suggests that the question itself might be based on false distinctions. Design and emergence, intention and mechanism, consciousness and unconscious process, these might be different aspects of the same underlying phenomenon rather than fundamentally different categories. Whether Earth's habitability reflects conscious design, emergent self-organization, or something that transcends both categories, what's clear is that we live in a reality that supports not just existence but reflection on existence. Not just matter but minds capable of understanding matter. Not just process but consciousness capable of contemplating process. That capacity for contemplation might be the most remarkable feature of our situation, regardless of how it came to be. We are arrangements of atoms that can think about atoms, products of evolution, that can understand evolution, possibly simulated beings capable of questioning the nature of simulation. The questions we've been exploring about design and emergence, Intention and accident, meaning and mechanism, are questions that the universe is asking about itself through us. We are its instruments of self-reflection, its means of understanding its own nature and possibilities. Whether that makes us the purpose of cosmic evolution or simply one of its more interesting byproducts, it certainly makes our existence and our capacity for wonder something worth celebrating, protecting, and extending as far as our intelligence can carry us. The more we examine the specific conditions that make Earth habitable, the more we encounter phenomena that seem balanced on knife edges, parameters that could easily have been different in ways that would make complex life impossible. This apparent fine-tuning shows up at every scale, from fundamental physics to planetary dynamics to biological systems. Consider the mass of the proton. If it were just 0.2% larger, hydrogen atoms would be unstable, and stars couldn't form. If it were smaller by a similar amount, neutrons would decay too quickly for nuclei to hold together. The entire periodic table of elements depends on this precise balance. The strength of the electromagnetic force, if it were slightly stronger, atoms wouldn't form, slightly weaker, and nuclear reactions couldn't occur. The ratio between electromagnetic and gravitational forces has to fall within an extremely narrow range for both stars and planets to exist. The cosmological constant, the energy density of empty space that drives cosmic expansion, appears to be fine-tuned to within 1 part in 10 circumflex 120. That's a degree of precision that defies intuitive understanding. If it were larger, space would expand so rapidly that matter couldn't clump together to form structures. If it were smaller or negative, the universe might collapse before complexity could develop. Even the number of spatial dimensions seems optimized for complexity. In fewer than 3 dimensions, complex structures can't form. In more than 3 dimensions, atoms and planetary orbits become unstable. We live in exactly the dimensionality that allows for maximum complexity and stability. Moving from fundamental physics to planetary conditions, the fine-tuning continues. Earth's distance from the Sun is precise to within a few percent. Closer and water would vaporize. Farther and it would freeze. The planet's mass is just right. Larger and it would retain too much atmosphere. Smaller and it would lose atmosphere to space. The Moon's size and distance are crucial for climate stability. Too large or too close, and tidal forces would be catastrophic. Too small or too distant, and Earth's axial tilt would vary chaotically. The collision that likely formed the Moon had to occur at exactly the right angle and speed, parameters that required extraordinary precision. Earth's magnetic field depends on the planet's size, composition, and rotation rate, all of which had to fall within narrow ranges. The concentration of radioactive elements in Earth's interior provides just enough heat to drive plate tectonics, without making the surface uninhabitably hot. The composition of Earth's atmosphere is maintained by biological and geological processes working in concert. Oxygen levels high enough to support complex metabolism, but low enough to prevent uncontrollable combustion. Carbon dioxide levels that maintain a modest greenhouse effect without runaway heating. Water vapor that creates clouds and precipitation without overwhelming the system. Even the timing of major evolutionary developments shows apparent fine-tuning. The emergence of photosynthesis occurred early enough to transform the atmosphere before complex life needed oxygen. The development of multicellular organisms happened when ocean chemistry and climate conditions were suitable for supporting them. The evolution of intelligence occurred during a period of relative planetary stability. The asteroid impact that ended the dinosaur era happened at a time when mammalian evolution could take advantage of the ecological opportunities it created. Earlier, and mammalian lineages might not have been ready to diversify. Later, and dinosaurs might have evolved intelligence first. Biological systems themselves show multiple levels of fine-tuning. The genetic code appears to be optimized for error tolerance. Changes in DNA sequences are less likely to produce catastrophic changes in protein function than would be true for most alternative codes. The structure of DNA is precisely suited for both information storage and replication accuracy. Protein structures depend on forces that are balanced to within very narrow margins. Stronger intramolecular forces and proteins wouldn't fold properly. Weaker forces, and they wouldn't maintain stable shapes. The strength of hydrogen bonds, the behavior of hydrophobic interactions, the flexibility of chemical bonds, all seem calibrated for maximum functionality. Even consciousness appears to depend on precise neural timing and chemical balance. Neurotransmitter concentrations, synaptic delays, neural network architectures, small changes can dramatically affect cognitive function. The brain operates near the edge of chaos, organized enough for stable information processing, but flexible enough for learning and adaptation. Each instance of apparent fine-tuning could potentially be explained away. Perhaps we're in a multiverse where every possible combination of parameters exists somewhere, and we naturally find ourselves in the rare universe where they support observers. Perhaps there are deeper physical principles that necessitate these particular values. Perhaps our perspective is biased by the fact that we can only observe conditions compatible with our existence. But when you consider all these instances together, fundamental constants, planetary parameters, atmospheric composition, biological systems, evolutionary timing, neural organization, the cumulative impression is striking. It's not just that life is possible in our universe, it's that so many independent factors seem calibrated to support not just basic existence, but the development of complexity, intelligence, and consciousness. This doesn't prove design in any traditional sense, but it does suggest that our existence depends on an extraordinary convergence of favorable conditions. Whether that convergence represents intention, selection from among many possibilities, or the operation of deeper organizing principles, it's certainly remarkable enough to deserve careful consideration. The fine-tuning also raises questions about responsibility. If we are the beneficiaries of such precisely calibrated conditions, if our existence depends on the convergence of so many favorable factors, what obligations does that place on us? How should we respond to the apparent rarity and fragility of the circumstances that make consciousness possible? These aren't just scientific questions, they're ethical and existential ones. If Earth represents something genuinely special in the cosmic landscape, if the conditions that support reflective intelligence are as rare and delicate as they appear, then perhaps our primary obligation is to protect and extend those conditions for as long as possible. That might mean preserving Earth's habitability through careful environmental stewardship. It might mean spreading life and intelligence to other worlds to reduce the risk of single-point failure. It might mean developing technologies that can maintain complex systems even as natural conditions change. But it definitely means recognizing that consciousness, the capacity to reflect on existence, to ask questions about meaning and purpose, to contemplate the nature of reality itself, might be among the most valuable and fragile phenomena in the universe. We may be the universe becoming aware of itself, and that awareness carries both privilege and responsibility. The fine-tuning of physical constants and planetary conditions provides the foundation for complexity. But complexity alone isn't enough to guarantee the emergence of life. Something else had to happen: the transition from non-living chemistry to self-replicating, evolving systems. And when we examine what that transition required, we encounter another layer of apparent precision and timing. Life as we know it depends on carbon-based chemistry, and carbon is perfectly suited for the role. It forms strong, stable bonds with other elements, while remaining flexible enough to participate in the complex molecular rearrangements that metabolism requires. It can create long chains, branch structures, rings, three-dimensional frameworks, the architectural diversity that complex chemistry needs. But carbon had to be available in sufficient quantities, and that required the right kind of stellar evolution. Carbon is produced in stellar cores through the triple alpha process, where 3 helium nuclei combine to form carbon. This process depends critically on the existence of a specific energy level in the carbon nucleus, a level that wouldn't exist if the strong nuclear force were even slightly different. The physicist Fred Hoyle predicted the existence of this energy level based purely on the fact that carbon exists in the universe. reasoning that stellar nucleosynthesis couldn't produce carbon without it. When experiments confirmed his prediction, Hoyle famously remarked that it looked like a superintellect had monkeyed with physics. Whether or not you accept that interpretation, the precision required for carbon production is striking. Once carbon was available, it had to be delivered to planetary surfaces in forms that could participate in complex chemistry. This likely occurred through a combination of processes: accretion during planetary formation, delivery by comets and asteroids, outgassing from planetary interiors. The timing and intensity of these processes had to fall within narrow ranges, enough to provide essential elements without overwhelming planetary development. The early Earth environment also had to support the formation of complex organic molecules. This required liquid water, but water alone isn't sufficient. The pH had to be appropriate, the temperature range suitable, the chemical environment neither too oxidizing nor too reducing. Concentrating mechanisms were needed to bring dilute organic compounds together in sufficient densities for interaction. Many researchers believe that life originated in specialized environments, perhaps around hydrothermal vents, in tidal pools within mineral matrices that could concentrate and organize organic molecules. These environments had to provide the right combination of energy sources, chemical gradients, and physical conditions for the emergence of self-replicating systems. The transition from complex chemistry to true life required the development of several key capabilities: information storage, replication with variation, metabolism that could extract energy from the environment, and some form of boundary that separated the internal chemistry of early cells from their surroundings. DNA and RNA provide the information storage and replication capabilities that life requires, but these molecules are themselves quite complex. RNA in particular seems almost designed for its biological roles. It can store information like DNA, catalyze reactions like enzymes, and regulate gene expression in ways that modern cells depend on. The idea that RNA preceded DNA in early evolution, the RNA world hypothesis, suggests that this single molecule could have provided all the basic functions needed for primitive life. But functional RNA molecules are difficult to synthesize under prebiotic conditions and tend to degrade rapidly in aqueous environments. The conditions that would allow RNA to persist long enough to evolve are quite specific. The development of cellular membranes required molecules that could spontaneously form stable boundaries while allowing selective transport of materials in and out. Lipid bilayers have exactly these properties, but only certain types of lipids can form stable membranes under early Earth conditions. Metabolism posed its own challenges. Early life needed energy sources that were available in the absence of oxygen, and it needed biochemical pathways that could extract that energy efficiently. Many of the metabolic pathways used by modern organisms are extraordinarily complex, involving dozens of enzymes working in precise sequence. Even the simplest known life forms today are remarkably sophisticated. The smallest bacterial genomes contain hundreds of genes encoding proteins essential for replication, metabolism, and basic cellular functions. It's difficult to imagine how systems this complex could have arisen through undirected chemical processes alone. This has led some scientists to propose that life might have originated through multiple independent events rather than a single genesis, that different aspects of cellular organization developed separately and then combined. Others suggest that life might have originated in environments very different from anything that exists on Earth today, perhaps in the interior of comets, around deep-sea vents, or even in space itself. There's also the possibility that life didn't originate on Earth at all, that it arrived from elsewhere in the universe through a process called panspermia. This doesn't solve the origin problem, it just moves it to another location, but it might explain how complex life could appear relatively early in Earth's history without requiring extremely rapid evolution from non-living precursors. Once life did emerge, its subsequent evolution shows patterns that are difficult to explain through purely random processes. Major evolutionary innovations, photosynthesis, eukaryotic cells, multicellularity, sexual reproduction, nervous systems, all appear to have developed relatively quickly once the appropriate conditions were established. These innovations often required multiple coordinated changes that had to occur nearly simultaneously to be functional. Photosynthesis requires dozens of different proteins working together in precise spatial arrangements. Eukaryotic cells needed mechanisms for controlling gene expression, organizing internal structure, and coordinating cell division. Sexual reproduction required the evolution of compatible mating systems in both partners. The probability that such complex innovations could arise through random mutation and selection alone is a subject of ongoing scientific debate. Some argue that the appearance of rapid innovation reflects gaps in the fossil record rather than accelerated evolution. Others suggest that evolution itself might involve non-random processes that bias mutation and selection toward functional outcomes. Regardless of the specific mechanisms involved, the history of life on Earth shows a clear trend toward increasing complexity, intelligence, and awareness. Simple prokaryotic cells gave rise to complex eukaryotic cells, which gave rise to multicellular organisms, which gave rise to nervous systems, which gave rise to brains capable of consciousness and reflection. This progression isn't inevitable. There's no physical law that requires evolution to produce intelligence, but it's what happened on Earth, and it happened relatively quickly given the timescales involved. The transition from the first primitive cells to modern human consciousness occurred in less than 4 billion years, a brief moment in cosmic history. Whether this represents the unfolding of built-in potentials in matter and energy, the action of selective pressures that favor complexity, or the operation of organizing principles we don't yet understand, it's certainly one of the most remarkable phenomena we know of. The emergence of minds capable of contemplating their own existence from arrangements of atoms that were once scattered in interstellar space. The question of whether this process was guided or emergent, intentional or accidental, designed or discovered, remains open. But the fact that it occurred at all, and occurred in ways that produced beings capable of asking such questions, is perhaps the most compelling evidence we have that reality is stranger and more wonderful than our ordinary categories of understanding can capture. As we reach the end of this exploration, we find ourselves not with definitive answers but with deepened appreciation for the questions themselves. The inquiry into whether Earth was designed has taken us through physics and biology, astronomy and chemistry, philosophy and mathematics, and at each level we've encountered patterns that invite wonder. Whether these patterns reflect intention or emergence, design or self-organization, they clearly demonstrate that our universe is far from random. From the precise values of fundamental constants to the intricate machinery of biological cells, from the delicate balance of planetary systems to the remarkable properties of consciousness itself, we inhabit a reality that seems systematically organized toward complexity, intelligence, and the capacity for reflection. This doesn't prove that Earth was designed in any traditional sense of conscious planning and execution, but it does suggest that the categories of designed and accidental, intentional and random might not fully capture the nature of what we observe. Perhaps reality operates according to principles that transcend these distinctions, principles that favor the emergence of organization, beauty and awareness through processes that look designed even when they aren't consciously directed. The question itself, what if Earth was designed, has value independent of any specific answer. It invites us to notice the remarkable suitability of our world for life, consciousness, and contemplation. It encourages us to pay attention to the intricate relationships between planetary systems and biological processes. It asks us to consider our responsibilities as beneficiaries of conditions that appear to be extraordinarily rare and precious. If we are the product of cosmic accident, then consciousness represents an incredible stroke of fortune, the universe becoming aware of itself through arrangements of matter that have no right to be as remarkable as they are. If we are the product of deeper organizing principles, then consciousness might represent the universe fulfilling its inherent potential for self-awareness and understanding. If we are living in a designed reality, whether through divine intention, natural principles, or computational simulation, then consciousness might be the purpose toward which that design was directed. A means for existence to know itself, appreciate itself, and take responsibility for its own continuation and flourishing. Each perspective carries its own implications for how we should live, what we should value, and how we should relate to the world that sustains us. But all perspectives converge on certain recognitions that consciousness is precious, that Earth's habitability is remarkable, that our existence depends on countless favorable conditions operating in concert across multiple scales of space and time. The patterns we've explored, orbital mechanics and atmospheric chemistry, molecular biology and quantum physics, evolutionary history and cosmic fine-tuning, all point toward the same basic conclusion. We live in a universe where matter and energy organize themselves in ways that support not just existence, but reflection on existence. Not just life, but intelligence. Not just intelligence, but the capacity to contemplate meaning, purpose, beauty, and truth. Whether this represents design or discovery, intention or emergence, purpose or accident, it's certainly remarkable enough to inspire gratitude, humility, and care. We are the universe contemplating itself, and that contemplation reveals a reality more intricate, more balanced, and more conducive to consciousness than pure chance would seem to allow. The scientific frameworks we use to understand natural processes, evolution, stellar nucleosynthesis, planetary formation, biochemistry, don't require us to invoke design or intention. They work perfectly well as descriptions of mechanism and process, but they also don't preclude the possibility that those mechanisms and processes operate within larger frameworks of organization and meaning. Perhaps the most honest response to what we've discovered is a kind of informed wonder, appreciation for the extraordinary conditions that make our existence possible, combined with humility about the ultimate nature and purpose of those conditions. We can map the mechanisms without fully understanding the principles. We can trace the processes without knowing their destination. What we can do is pay attention to the intricate beauty of the world that sustains us, to the delicate balances that maintain habitability, to the remarkable fact that arrangements of matter can become aware of their own existence and contemplate their own meaning. Whether Earth was designed or not, we are here now, thinking, wondering, taking responsibility for our impact on the systems that support us. We are the planet's way of knowing itself and perhaps its best hope for long-term care and protection. The question we began with, what if Earth was designed, has led us through territories of science and philosophy, mechanism and meaning, process and purpose. We end not with certainty but with appreciation for the questions themselves, for the capacity to ask them, and for the remarkable reality that makes such questioning possible. The stars continue their ancient dance. The planet continues its rotation. The atmosphere continues its circulation. The biosphere continues its intricate cycles of growth and renewal. And consciousness continues its patient work of trying to understand what it all means. Grateful for the opportunity to wonder, humbled by the complexity of what we're trying to understand, committed to protecting the conditions that make such understanding possible. Whether by design or emergence, intention or accident, we are here, and that itself is cause for wonder, gratitude, and the kind of careful attention that treats existence as the precious and perhaps improbable gift it appears to be. Thanks for joining this exploration, for following the questions wherever they led, for holding space for uncertainty, while appreciating the remarkable patterns that surround us. The universe continues its unfolding, and through our consciousness, it continues to discover what it is and what it might become. Sleep well, or think long. There's no pressure either way. The planet will keep turning, the patterns will continue their ancient dance, and the questions, the good ones, the deep ones, the ones that connect us to something larger than ourselves, will still be here when you're ready to explore them further. When we think about time on Earth, we usually think in human scales. Minutes, hours, days, the rhythms that structure our daily experience. But the planet operates on vastly different timescales, and it's in those deeper rhythms that some of the most remarkable patterns emerge. patterns that suggest coordination across periods so vast that they challenge our ordinary sense of cause and effect. Consider the carbon cycle, not just the seasonal exchange of CO2 between plants and atmosphere, but the geological carbon cycle that operates over millions of years. Carbon gets locked away in limestone and organic sediments, then released through weathering and volcanic activity. The rate of this cycling responds to global temperature. Faster weathering during warm periods pulls more carbon out of the atmosphere, while slower weathering during cool periods allows carbon to accumulate. It's a thermostat that operates over geological time, crude by engineering standards, but effective at preventing Earth from freezing solid or boiling away. The system has maintained global temperatures within a range compatible with liquid water for billions of years, through ice ages and greenhouse periods, asteroid impacts and volcanic episodes, the rise of photosynthesis and the emergence of complex life. No central control mechanism orchestrates this regulation, yet the planet somehow maintains the conditions that life requires. Ocean chemistry responds to atmospheric changes. Weathering rates adjust to temperature variations. Biological processes adapt to shifting environmental conditions. The whole system exhibits a kind of planetary homeostasis, not perfect stability, but bounded variation around states that support complexity and life. This apparent self-regulation extends to other cycles as well. The nitrogen cycle moves this essential element between atmosphere, soil, and living tissue through processes involving bacteria, plants, decomposition, and atmospheric chemistry. The phosphorus cycle circulates this crucial component of DNA and cellular energy systems through weathering, biological uptake, and sedimentation. Each cycle operates on its own timescales, some fast, some slow, some intermediate, but they all interact in ways that maintain overall system stability. When one cycle shifts, others respond in ways that often moderate the change rather than amplifying it. It's as if the planet has built-in feedback mechanisms that resist extreme departures from life-supporting conditions. The timing of major evolutionary innovations also shows patterns that are difficult to explain through pure chance. Photosynthesis emerged early enough to transform the atmosphere before complex life needed oxygen. Eukaryotic cells developed when chemical conditions favored the endosymbiotic partnerships that created them. Multicellular life appeared when ocean chemistry and climate stability could support it. The Cambrian explosion, that remarkable burst of evolutionary innovation about 540 million years ago, occurred when atmospheric oxygen reached levels that could support complex metabolism, when ocean chemistry favored biomineralization, when genetic toolkit genes had evolved to control body plan development. Multiple factors converged within a relatively narrow time window to enable the rapid diversification of complex life forms. Even mass extinctions, those apparent catastrophes that wiped out dominant life forms, often created opportunities for evolutionary innovations that might not have occurred otherwise. The extinction that ended the Permian period eliminated many established ecosystems, but it also opened ecological niches that allowed dinosaurs to evolve and diversify. The asteroid impact that ended the Cretaceous cleared the way for mammalian radiation and eventually human evolution. These events weren't planned or coordinated, but their timing often seems fortuitous for the long-term development of complexity and intelligence, as if the planet somehow knows when to shake things up and when to maintain stability, when to preserve existing systems and when to allow them to be replaced by something new. The development of intelligence itself shows this same pattern of apparent coordination. Brains evolved independently multiple times, invertebrates, arthropods, cephalopods. Each lineage developed neural solutions appropriate to their ecological challenges, but all converged on similar principles of information processing, learning, and behavioral flexibility. Human intelligence emerged during a period of climate instability that favored adaptability over specialized adaptation. Ice ages and interglacials created environmental challenges that selected for cognitive flexibility, tool use, social cooperation, and communication. The same climatic variations that might have driven many species extinct provided the selective pressures that shaped human consciousness. Even the timing of human cultural evolution shows remarkable coordination. Agriculture developed independently in multiple regions within a few thousand years of each other, just as the climate was stabilizing after the last ice age. Writing systems emerged in several civilizations around the same time. The scientific revolution, the industrial revolution, the information revolution, all occurred when the necessary preconditions had aligned. It's as if the planet has been preparing for the emergence of a species capable of understanding and potentially managing planetary systems. Human technology now affects global climate, ocean chemistry, atmospheric composition, biological diversity. We've become a geological force, but we've also developed the capacity to study and potentially regulate our own impact. This transition from unconscious planetary regulation to potentially conscious planetary management represents a new phase in Earth's history. For the first time, a species has emerged that can understand the global systems that sustain life and potentially take responsibility for maintaining them. Whether this represents the intended outcome of some vast design, the inevitable result of evolutionary processes, or an unprecedented accident with uncertain consequences, we're clearly living through a remarkable transition. The planet that gave rise to consciousness is now dependent on consciousness for its continued habitability. The deep time patterns we observe, the coordination of cycles and events across geological timescales, suggest that Earth's history isn't random. Whether driven by inherent organizing principles, emergent system properties, or intentional guidance, the planet has maintained conditions suitable for increasing complexity and eventual self-awareness. And now that self-awareness faces the question of how to use its newfound power responsibly, we are the planet becoming conscious of itself, and that consciousness carries both extraordinary privilege and extraordinary responsibility for what happens next. The rhythm of time on Earth, from millisecond neural firings to billion-year geological cycles, all seems coordinated in ways that support the emergence and maintenance of life, complexity, and ultimately the consciousness that allows us to perceive these patterns and ask what they might mean. Whether by design or emergence, intention or accident, we find ourselves embedded in temporal patterns that span scales from quantum to cosmic, all apparently organized toward outcomes that support reflection, understanding, and the capacity to appreciate the remarkable nature of existence itself. As we delve deeper into the question of whether Earth shows signs of design, we encounter layers of complexity that extend far beyond what meets the eye. The more precisely we examine the conditions that support life, the more we discover relationships and dependencies that seem almost impossible to account for through chance alone. Consider the relationship between Earth's size and its ability to maintain the conditions life requires. The planet had to be large enough to retain a substantial atmosphere and generate a protective magnetic field through geological time, but not so large that surface gravity would crush complex life forms or that atmospheric pressure would become toxic. Earth's mass is about 5.97 quarts 10 circumflex, 24 kilograms, a number that might seem arbitrary but turns out to be crucial for habitability. If Earth were significantly smaller, say Mars-sized, it would have cooled too quickly for plate tectonics to persist. The magnetic field would have failed early in planetary history, allowing solar wind to strip away the atmosphere. Surface gravity would be too weak to retain water vapor and other light gases essential for climate regulation. If Earth were much larger, approaching the size of Neptune or Uranus, it would likely have retained the hydrogen and helium from the solar nebula, becoming a gas giant unsuitable for surface life. Even a moderately larger rocky planet would have crushing surface gravity, dense atmosphere, and intense greenhouse heating that would make complex life impossible. The precise mass that Earth ended up with allows for stable plate tectonics that recycle surface materials and regulate global temperature, strong enough magnetic field generation to protect the atmosphere, optimal surface gravity for retaining essential atmospheric gases, while allowing complex organisms to function, and just the right balance of atmospheric pressure and greenhouse heating to maintain liquid water across most of the surface. This Goldilocks relationship extends to Earth's internal structure and composition. The planet's core contains just the right amount of iron and nickel to generate a strong magnetic field, but not so much that the surface would be constantly bombarded with volcanic activity. The mantle has the right viscosity to drive plate tectonics at a rate that recycles carbon and nutrients without making the surface geologically chaotic. The crust contains the right mix of heavy and light elements to support both continental landmasses and ocean basins. Too much heavy material and the surface would be uniformly covered by deep oceans. Too much light material, and there would be no ocean basins to moderate climate and support marine ecosystems. Even the distribution of radioactive elements in Earth's interior seems calibrated for long-term habitability. These elements provide the heat that drives geological processes, but their concentrations are precisely balanced. Too little radioactive heating and the planet would have become geologically dead like Mars. Too much and the surface would be constantly reworked by volcanism and tectonism. The timing of radioactive decay also matters. Elements like uranium-235 and potassium-40 have half-lives that allowed them to provide substantial heating during Earth's early history, when geological activity was most important for establishing stable surface conditions, while gradually declining to levels that maintain current geological processes without overwhelming them. This extends to the chemical composition of Earth's surface environments. The pH of the oceans, currently about 8.1, is maintained within a narrow range that supports both carbonate shell formation and the dissolution of nutrients from rocks. If ocean pH were significantly higher or lower, marine ecosystems would collapse and the carbon cycle would be disrupted. Atmospheric chemistry shows similar precision. The partial pressure of oxygen, currently about 21% of total atmospheric pressure, is high enough to support efficient cellular respiration in complex organisms, but not so high that fires would be uncontrollable. The balance between oxygen and carbon dioxide maintains photosynthesis and respiration in dynamic equilibrium. Water vapor concentrations in the atmosphere create just enough greenhouse warming to keep the planet habitable, but not so much as to trigger runaway greenhouse heating like Venus. Cloud formation provides negative feedback that moderates temperature increases. More heating leads to more evaporation and cloud cover, which reflects more sunlight back to space. The nitrogen that makes up 78% of the atmosphere serves multiple crucial functions. It dilutes oxygen to prevent combustion hazards, provides raw material for amino acid and nucleic acid synthesis, and creates atmospheric pressure that allows liquid water to exist across a wide temperature range. Nitrogen is chemically inert enough to remain stable in the atmosphere, but reactive enough to participate in biological nitrogen fixation. Even trace atmospheric gases play essential roles. Argon makes up less than 1% of the atmosphere but contributes to total atmospheric pressure. Carbon dioxide is only 0.04%, but drives photosynthesis and climate regulation. Ozone in the stratosphere is measured in parts per million, but provides essential protection from ultraviolet radiation. The hydrological cycle that moves water between oceans, atmosphere, and land depends on precise relationships between temperature, pressure, and the physical properties of water. If water's heat of vaporization were different, if its vapor pressure behavior were altered, if its viscosity or surface tension properties were changed, the circulation patterns that distribute fresh water and moderate climate would not function properly. Ocean circulation itself depends on precise relationships between temperature, salinity, and density. The thermohaline circulation that moves warm water toward the poles and cold water toward the equator is driven by small differences in water density that depend critically on the exact properties of seawater. Change the freezing point or density relationship slightly, and global heat transport would be disrupted. The seasonal cycles that drive biological rhythms depend on Earth's axial tilt being stable within a narrow range. Too little tilt, and there would be no seasons. Tropical regions would remain hot while polar regions stayed frozen year-round. Too much tilt and seasonal temperature swings would be so extreme that large regions would alternate between being uninhabitable in summer and winter. The moon's stabilizing influence on this tilt requires the satellite to be just the right size and distance. Closer and tidal forces would be catastrophic. Farther and the stabilization would be ineffective. The moon is currently about 384,400 kilometers away, a distance that creates substantial tides without overwhelming coastal ecosystems, and maintains long-term climate stability without locking Earth into rigid rotation. Even the length of Earth's day seems optimized for life. At 24 hours, it's long enough to allow substantial photosynthesis during daylight hours, but short enough to prevent extreme temperature differences between day and night sides. The rotation rate affects atmospheric circulation patterns, ocean current strength, and the behavior of weather systems in ways that all contribute to climate stability. The planet's orbital characteristics show similar apparent fine-tuning. Earth's orbital eccentricity, the degree to which its path around the Sun deviates from a perfect circle, is currently about 0.017, which means the planet receives only about 6% more solar energy at its closest approach to the Sun than at its farthest point. This minimal variation prevents extreme seasonal climate swings while still providing enough orbital variation to drive the Milankovitch cycles that regulate ice ages. The timing of perihelion, Earth's closest approach to the Sun, currently occurs in early January during Northern Hemisphere winter. This means the hemisphere with most of the planet's landmass receives maximum solar energy when it's tilted away from the Sun, moderating seasonal temperature extremes. If perihelion occurred during Northern Hemisphere summer, seasonal contrasts would be much more severe. Earth's position in the solar system also affects its habitability in ways that extend beyond simple distance from the Sun. The planet's location shields it from much of the cosmic debris that exists in the outer solar system while keeping it far enough from the Sun to avoid the intense radiation and gravitational disturbances that affect Mercury and Venus. Jupiter's massive gravitational field acts as a cosmic vacuum cleaner, capturing or deflecting comets and asteroids that might otherwise impact Earth. The gas giant's position and orbital characteristics create a dynamic stability in the inner solar system that has protected Earth from catastrophic bombardment throughout most of its history. Even the asteroid belt between Mars and Jupiter represents a form of cosmic organization that supports Earth's habitability. If that material had coalesced into a planet, gravitational interactions might have destabilized Earth's orbit. If it had been scattered throughout the inner solar system, constant impacts would have prevented the development of complex life. The timing of major impact events in Earth's history also shows apparent coordination with evolutionary developments. The late heavy bombardment about 4 billion years ago delivered water and organic compounds when the planet was ready to incorporate them into surface environments. The Chicxulub impact 66 million years ago eliminated dinosaurs just as mammalian lineages were developing the characteristics that would allow them to diversify and eventually give rise to human intelligence. This extends to smaller-scale environmental factors that affect biological systems. The intensity and spectrum of solar radiation that reaches Earth's surface is precisely calibrated for photosynthesis, energetic enough to drive the chemical reactions that create organic compounds from carbon dioxide and water, but not so intense as to damage the molecular machinery that carries out these reactions. The transparency of the atmosphere in visible wavelengths allows sunlight to reach Earth's surface and penetrate into ocean waters where photosynthetic organisms can function. The absorption of ultraviolet wavelengths by ozone protects DNA and other biological molecules from radiation damage. The greenhouse absorption of infrared wavelengths by water vapor and carbon dioxide maintains surface temperatures within the range where liquid water can exist. Even the chemical properties of the elements that life depends on seem optimized for biological function. Carbon forms strong, stable bonds that can create the complex molecular structures that store genetic information and catalyze biochemical reactions. Nitrogen provides the chemical basis for amino acids and nucleic acids. Oxygen enables efficient energy metabolism while remaining reactive enough to participate in diverse chemical processes. Phosphorus creates the high-energy bonds that power cellular processes and forms the backbone of DNA and RNA. Sulfur contributes to protein structure and participates in important metabolic reactions. Calcium provides structural support and plays crucial roles in cellular signaling. Iron enables oxygen transport and electron transfer reactions. The availability of these elements in Earth's surface environments depends on geological processes that concentrated them from the diffuse distributions that existed in the early solar system. Differentiation during planetary formation created iron-rich cores and silicate mantles. Weathering and erosion concentrated essential elements in ocean water and sedimentary rocks. Biological processes further concentrated and organized these materials into forms that support complex chemistry. The stability of the chemical compounds that life depends on requires precise relationships between temperature, pressure, and chemical environment. Proteins maintain their three-dimensional structures within narrow ranges of pH and temperature. DNA remains stable enough to store genetic information reliably, while remaining flexible enough to allow replication and transcription. Cell membranes maintain selective permeability that allows controlled exchange of materials between cellular interiors and external environments. Even the quantum mechanical properties that govern atomic behavior seem fine-tuned for the chemistry that life requires. The strength of electromagnetic interactions determines how tightly electrons are bound to atomic nuclei, affecting the energy required for chemical reactions and the stability of molecular bonds. The exclusion principle that prevents electrons from occupying the same quantum states creates the electron shell structure that determines chemical bonding patterns. The masses of fundamental particles affect the behavior of atoms and molecules in ways that influence biological chemistry. If protons were slightly heavier, hydrogen would be unstable. If electrons were slightly heavier, atoms would be smaller and chemical bonds would behave differently. If neutrons were not slightly heavier than protons, nuclear physics would not allow the formation of complex elements. These quantum mechanical relationships cascade upward through atomic chemistry, molecular biology, cellular processes, organismal function, ecosystem dynamics, and ultimately planetary habitability. Small changes in fundamental physics would create large changes in the possibility of complex life, suggesting that our existence depends on an extraordinary convergence of favorable conditions at every level of organization. The precision required for this convergence, and the fact that we observe it despite the vast range of alternative possibilities, continues to challenge our understanding of whether such coordination could arise through purely random processes, or whether it might reflect deeper organizing principles that favor the emergence of complexity, life, and consciousness. The interconnections between these various levels of organization, from quantum mechanics to planetary dynamics, create what systems theorists call nested hierarchies of structure and function. Each level operates according to its own principles while being constrained by the levels below and influencing the levels above. The result is a kind of cosmic architecture that supports the emergence of increasingly complex forms of organization. Whether this architecture represents design, emergence, or some synthesis of both, it certainly provides the framework within which consciousness can arise and contemplate its own existence. We are embedded in these nested hierarchies, products of them, and now potentially conscious participants in their ongoing evolution. The more we understand about the conditions that make our existence possible, the more remarkable it appears that such conditions exist at all. Whether by intention or accident, design or discovery, we find ourselves in a universe that seems systematically organized to support not just matter and energy, but information, complexity, life, and ultimately the consciousness that allows reality to know itself. As we examine the molecular foundations of life, the biochemical processes that sustain every living cell, we encounter another level of apparent design that operates at scales far smaller than anything visible to human eyes. Here, in the realm of proteins and nucleic acids, chemical reactions and energy transfers, we find machinery that exhibits the precision and coordination we associate with the most sophisticated human technologies. Consider the ribosome, the molecular machine that translates genetic information into proteins. This cellular component reads the sequence of nucleotides in messenger RNA and assembles amino acids in the precise order specified by the genetic code. The process requires coordination between dozens of different molecules, each performing specific functions with extraordinary precision. The ribosome must bind to messenger RNA at exactly the right location, recognize start codons that indicate where protein synthesis should begin, move along the RNA strand in precise 3 nucleotide steps, recruit transfer RNA molecules that carry the correct amino acids, catalyze the formation of peptide bonds between successive amino acids, and release the completed protein when it encounters stop codons. Each step involves molecular recognition events that depend on the 3-dimensional shapes of interacting molecules, shapes that must complement each other with lock-and-key precision. The ribosome can distinguish between transfer RNA molecules that differ by only a single nucleotide, ensuring that the correct amino acid is incorporated at each position in the growing protein chain. The fidelity of this process is remarkable. Translation errors occur only about once in every 10,000 amino acids incorporated, a level of accuracy that rivals the best human manufacturing processes. This precision is maintained despite the random thermal motion that constantly threatens to disrupt molecular interactions, and despite the fact that the chemical differences between some amino acids are quite subtle. Even more remarkable is the fact that ribosomes can synthesize proteins at extraordinary speed, incorporating hundreds of amino acids per minute, while maintaining this high level of accuracy. The process involves multiple quality control mechanisms that check the accuracy of each step and reject incorrect selections before they can be incorporated into the growing protein. The genetic code itself shows evidence of optimization that suggests more than random evolution. The mapping between 3 nucleotide codons and amino acids appears to minimize the effects of mutations. Changes in DNA sequences are less likely to produce catastrophic changes in protein function than would be true for most alternative codes. Related amino acids. Those with similar chemical properties tend to be encoded by similar codons that differ by only 1 nucleotide. This means that many single nucleotide mutations result in the substitution of one amino acid for another with similar properties, often preserving protein function even when the DNA sequence has changed. The redundancy built into the genetic code provides additional protection against mutation. There are 64 possible 3 nucleotide codons, but only 20 standard amino acids, so multiple codons specify the same amino acid. The pattern of this redundancy isn't random. It's organized in ways that provide maximum protection against the types of mutations that occur most frequently. Stop codons, the signals that terminate protein synthesis, are distributed through the code in ways that minimize the probability that a random mutation will accidentally create a premature stop signal. Start codons are sufficiently distinct from other codons that translation is unlikely to begin at incorrect locations. The universality of the genetic code. The fact that virtually all known life forms use the same mapping between codons and amino acids suggests that this system was established early in evolutionary history and has been preserved because of its efficiency and reliability. Alternative codes exist in some specialized contexts, but they represent minor variations on the universal theme. DNA replication shows similar evidence of sophisticated quality control mechanisms. The enzymes that copy DNA can detect and correct errors during the synthesis process, proofreading each newly incorporated nucleotide and removing it if it doesn't form proper base pairs with the template strand. Additional repair systems scan newly replicated DNA for errors that escaped proofreading and correct them before they can be passed on to daughter cells. The 3-dimensional structure of DNA, the famous double helix, provides both stability and accessibility for the molecular machines that must interact with genetic information. The two strands are held together by hydrogen bonds that are strong enough to maintain the structure, but weak enough to allow the strands to separate when DNA must be replicated or transcribed. The major and minor grooves of the double helix provide specific binding sites for proteins that must recognize particular DNA sequences without disrupting the overall structure. Regulatory proteins can read the chemical signatures of different nucleotide sequences by fitting into these grooves and making specific contacts with the edges of base pairs. The packaging of DNA within cell nuclei represents another level of sophisticated organization. Eukaryotic cells contain meters of DNA packed into nuclei only micrometers in diameter. This requires elaborate folding and organizing systems that make specific regions of the genome accessible when needed, while keeping the overall structure compact and protected. Histones, the proteins around which DNA is wrapped, don't just provide structural support. They also participate in gene regulation through chemical modifications that can turn genes on or off without changing the underlying DNA sequence. This epigenetic control system allows the same genome to produce many different cell types with distinct functions. The process of gene expression itself involves multiple levels of sophisticated control. Transcription factors must recognize specific DNA sequences and bind to them at exactly the right times and in the right combinations. RNA polymerase must transcribe genes at appropriate rates while maintaining high fidelity. The resulting RNA molecules must be processed, modified, and transported to the correct cellular locations. MicroRNAs and other regulatory molecules fine-tune gene expression by binding to specific messenger RNAs and affecting their stability or translation efficiency. This creates complex regulatory networks where the expression of one gene can affect the expression of many others, allowing cells to coordinate their responses to changing conditions. Protein folding represents perhaps the most remarkable example of biological precision and efficiency. A typical protein consists of hundreds of amino acids that must arrange themselves into exactly the right three-dimensional shape to function properly. The number of possible arrangements is astronomical, yet proteins find their correct conformations reliably and quickly. Molecular chaperones assist this process by providing controlled environments where folding can occur without interference from other cellular components. Quality control systems recognize misfolded proteins and either help them refold correctly or target them for destruction. The result is a cellular environment where thousands of different proteins maintain their proper shapes and functions simultaneously. Enzyme catalysis demonstrates how molecular structure enables sophisticated chemistry. Enzymes accelerate specific chemical reactions by factors of millions or billions while maintaining extraordinary selectivity, promoting desired reactions while suppressing unwanted side reactions. They achieve this through precisely shaped active sites that bind substrates in orientations that favor particular reaction pathways. The kinetics of enzyme action often show evidence of optimization, reaction rates that approach the theoretical limits imposed by molecular diffusion. Some enzymes have evolved to be catalytically perfect, meaning they catalyze reactions as fast as substrates can encounter them. This level of optimization suggests that natural selection has fine-tuned these systems to extraordinary levels of efficiency. Metabolic pathways that link multiple enzymatic reactions show similar evidence of optimization. The concentrations of metabolic intermediates are regulated to minimize waste and maximize efficiency. Branch points in metabolic networks are controlled to direct materials toward the products most needed under current conditions. Feedback loops prevent the overproduction of metabolites and maintain appropriate balances between different cellular processes. Cellular energy metabolism operates through molecular machines that convert chemical energy into forms that can power other cellular processes. ATP synthase, the enzyme that produces most cellular ATP, operates like a miniature turbine, using the flow of protons across cell membranes to drive the synthesis of high-energy phosphate bonds. The efficiency of this process approaches the theoretical limits of energy conversion, capturing more than 90% of the available chemical energy under optimal conditions. The molecular structure of ATP synthase shows evidence of sophisticated engineering, rotating components, proton channels, conformational changes that couple proton flow to ATP synthesis. Even the basic structure of cell membranes exhibits apparent design principles. Phospholipid bilayers form spontaneously in aqueous environments, but they create selectively permeable barriers that allow cells to maintain distinct internal chemistry while exchanging materials with their surroundings. Membrane proteins provide specific channels and pumps that regulate what enters and leaves the cell. The asymmetry of cell membranes, different compositions on the inner and outer surfaces, creates the electrochemical gradients that power many cellular processes. Maintenance of this asymmetry requires sophisticated transport systems that can distinguish between molecules that should and shouldn't cross the membrane. Signal transduction systems allow cells to detect, process, and respond to information from their environment. Receptor proteins recognize specific molecular signals and transmit information across cell membranes. Signal amplification systems can detect single molecules of some signaling compounds and translate them into cellular responses involving millions of molecules. These signal transduction networks exhibit properties we associate with sophisticated information processing systems, signal integration, noise filtering, amplification, memory, and adaptation. Cells can distinguish between different types of signals, integrate multiple inputs, and produce appropriate responses that depend on both current conditions and previous experiences. The molecular machinery of cell division ensures that genetic information is accurately transmitted to daughter cells. Chromosome condensation organizes DNA into compact structures that can be reliably separated. The mitotic spindle creates precisely aligned forces that pull sister chromosomes to opposite ends of the dividing cell. Checkpoints monitor the accuracy of each step and halt division if errors are detected. The timing and coordination of these processes prevents the genetic errors that would accumulate if cell division proceeded without proper controls. The molecular mechanisms that govern cell cycle progression show evidence of sophisticated regulatory logic that integrates information about cell size, DNA integrity, environmental conditions, and developmental signals. When we consider all of these molecular systems working together simultaneously in every living cell, the transcription and translation of genetic information, protein folding and enzymatic catalysis, energy metabolism and signal transduction, membrane transport and cell division, the level of coordination and precision is staggering. Each process depends on dozens or hundreds of different molecules interacting with extraordinary specificity and timing. The failure of any critical component would disrupt cellular function and potentially threaten the survival of the organism. Yet these systems operate reliably for years or decades in complex multicellular organisms, maintaining the precise chemical conditions that support consciousness and contemplation. The molecular foundations of life exhibit the hallmarks we associate with sophisticated engineering, modular design, error correction, quality control, optimization, and hierarchical organization. Whether these characteristics emerge through evolutionary processes, reflect deeper organizing principles, or represent some form of molecular-level design, they certainly provide a remarkable foundation for the complexity and consciousness that characterize life on Earth. The question of whether this molecular machinery was designed or discovered remains open, but the sophistication and efficiency of these systems continues to inspire both scientific inquiry and philosophical reflection about the nature of biological organization and the conditions that make complex life possible. The dance between order and chaos that characterizes Earth's systems becomes even more apparent when we examine the delicate balances that maintain planetary habitability across geological time. These aren't static equilibria, they're dynamic patterns that persist through constant change, adapting to perturbations while maintaining the overall conditions that complex life requires. Consider the intricate relationship between Earth's climate system and the global carbon cycle. Carbon moves constantly between atmosphere, oceans, land, and geological reservoirs through processes that operate on timescales from hours to millions of years. The rapid cycling involves photosynthesis and respiration, the dissolution and outgassing of CO2 in ocean water, the seasonal growth and decay of vegetation. But there's also a slower cycle that regulates long-term climate stability. When atmospheric CO2 levels rise, global temperatures increase, which accelerates the weathering of silicate rocks. This weathering consumes atmospheric CO2, pulling it out of the air and eventually depositing it in ocean sediments as limestone. The process provides negative feedback that prevents runaway greenhouse heating. When CO2 levels fall and temperatures drop, weathering slows down, allowing volcanic outgassing to gradually increase atmospheric CO2 concentrations and warm the climate. This geological thermostat has maintained Earth's surface temperature within the range where liquid water can exist for billions of years, despite variations in solar luminosity, volcanic activity, and biological productivity. The system isn't perfectly stable. Ice ages and greenhouse periods demonstrate that significant climate variations do occur, but these variations remain within bounds that allow life to persist and adapt. No runaway freezing like the Snowball Earth episodes that may have occurred early in planetary history. No runaway heating like the conditions that made Venus uninhabitable. Ocean chemistry shows similar patterns of dynamic stability. The pH of seawater is maintained around 8.1 through chemical buffering systems that resist acidification, but it's not rigidly fixed. Carbonate chemistry adjusts to changing atmospheric CO2 levels. Biological processes affect the concentration of nutrients and dissolved gases. Deep ocean circulation brings different water masses into contact and promotes chemical equilibration. The result is a marine environment that has supported life for billions of years while gradually evolving in response to changing planetary conditions. Early oceans were probably more acidic and had different chemical compositions, but they still provided suitable environments for the development of complex chemistry and early life. Atmospheric composition reflects an even more complex balance between geological, biological, and chemical processes. Oxygen levels are maintained around 21% through the balance between photosynthetic production and consumption by respiration, weathering, and volcanic reactions. This concentration supports efficient cellular metabolism without creating fire hazards that would make terrestrial life impossible. But oxygen levels have varied significantly over geological time. During the Carboniferous period, when vast coal deposits were being formed, atmospheric oxygen may have reached 35%, high enough to support giant insects and amphibians, but probably too high to be stable long-term. During other periods, oxygen levels dropped to levels that would challenge modern complex life. These variations demonstrate that Earth's atmospheric system can explore different stable states while maintaining overall habitability. The current composition isn't the only possible one, but it represents a configuration that supports extraordinary biological diversity and complexity. Nitrogen fixation provides another example of biological processes that maintain planetary habitability. Atmospheric nitrogen makes up 78% of the air, but is chemically inert, unavailable to most life forms in this gaseous state. Specialized bacteria convert atmospheric nitrogen into ammonia and nitrates that plants can use to synthesize amino acids and nucleic acids. Without nitrogen fixation, life would quickly exhaust the available supplies of this essential element. With too much nitrogen fixation, excess nutrients could disrupt ecosystem balance and lead to eutrophication of water bodies. The current rate of nitrogen fixation, regulated by the availability of energy and nutrients that nitrogen-fixing bacteria require, maintains a steady supply of biologically available nitrogen without overwhelming natural systems. Phosphorus cycling operates on different timescales but shows similar self-regulating properties. This element is essential for DNA, RNA, and cellular energy systems but exists in limited quantities. Weathering of rocks provides the primary source of phosphorus for biological systems, but the rate of this supply is slow enough that phosphorus often limits biological productivity. The scarcity of phosphorus may actually enhance ecosystem stability by preventing explosive population growth that could destabilize food webs. Organisms have evolved efficient mechanisms for recycling phosphorus, and this recycling helps maintain productive ecosystems even when external inputs are limited. Trace elements show similar patterns of biological regulation. Iron is essential for oxygen transport and many enzymatic reactions, but free iron is toxic in high concentrations. Biological systems have evolved sophisticated mechanisms for transporting and storing iron safely while making it available when needed. In ocean ecosystems, iron availability often limits phytoplankton growth, which affects the entire marine food web and influences global carbon cycling. The distribution of iron in ocean water depends on dust inputs from land, hydrothermal venting from the ocean floor, and biological processes that control iron speciation and availability. The water cycle that moves moisture between oceans, atmosphere, and land involves complex feedback relationships that help stabilize regional and global climate patterns. Evaporation from tropical oceans provides water vapor that releases latent heat when it condenses at higher latitudes, transferring energy from equatorial to polar regions and moderating temperature differences. Cloud formation provides negative feedback that limits temperature increases. More warming leads to more evaporation and cloud cover, which reflects more sunlight back to space. But cloud physics is complex. Different types of clouds have different effects on Earth's energy balance, and the relationships between temperature, humidity, and cloud formation involve many variables. Ice albedo feedback can either stabilize or destabilize climate depending on the circumstances. Ice and snow reflect sunlight, helping to keep polar regions cool, but if warming causes ice to melt, the exposed darker surfaces absorb more sunlight and accelerate warming. This positive feedback can lead to rapid transitions between different climate states. The current configuration of Earth's ice sheets and sea ice appears to be metastable, sensitive to perturbations but capable of persisting for thousands of years under stable conditions. Paleoclimate records show that ice sheet configurations have changed dramatically over geological time, but these changes usually occur over thousands to millions of years, giving ecosystems time to adapt. Biodiversity itself contributes to planetary stability through what ecologists call the insurance hypothesis. Ecosystems with many species are more resilient to perturbations because they contain multiple species that can perform similar ecological functions. If one species is eliminated by disease, climate change, or other disturbances, others can expand to fill its role. This biological redundancy operates at all scales from local ecosystems to global biogeochemical cycles. Multiple species contribute to nitrogen fixation, carbon sequestration, pollination, seed dispersal, and other ecosystem services. The diversity of life provides backup systems that help maintain ecological function even when individual species or populations are stressed. Predator-prey relationships, competitive interactions, and symbiotic partnerships create complex webs of dependency that can enhance ecosystem stability. No single species dominates completely. Even the most successful organisms are limited by resource availability, predation pressure, or competitive exclusion. These biological checks and balances help prevent any one species from overwhelming its environment. The evolution of cooperation and mutualism has created particularly stable biological partnerships. Lichens represent symbiosis between fungi and photosynthetic organisms that allows both partners to survive in environments where neither could exist alone. Mycorrhizal fungi form partnerships with plant roots that enhance nutrient uptake and stress resistance. Coral reefs depend on symbiosis between animals and photosynthetic algae. These cooperative relationships often enhance ecosystem stability by creating positive feedbacks that benefit multiple species simultaneously. Plants that form mycorrhizal partnerships are better able to survive drought and nutrient stress, which helps maintain forest ecosystems that provide habitat for many other species. The result of all these interacting cycles, feedbacks, and regulatory mechanisms is a planetary system that maintains habitable conditions while continuously evolving and adapting to changing circumstances. Earth's surface environment isn't static. It's a dynamic system that explores different configurations while remaining within the bounds that complex life requires. This apparent stability through change, homeostasis at the planetary scale, emerges from the interactions of countless individual processes that each follow simple physical, chemical, and biological rules. No central control system orchestrates these interactions, yet the overall behavior shows coordination and regulation that maintain global habitability. Whether this coordination represents an inherent property of complex systems, the result of evolutionary optimization, or evidence of deeper organizing principles, it certainly provides the stable foundation that allows consciousness to emerge and contemplate its own existence within these vast, interconnected cycles of matter and energy. The temporal rhythms that govern Earth's systems, from the rapid oscillations of ocean waves to the slow drift of continents, all seem to coordinate in ways that maintain conditions suitable for life, complexity, and ultimately the consciousness that can perceive and appreciate these remarkable patterns of organization. When we turn our attention to the emergence of intelligence itself, we encounter perhaps the most remarkable aspect of Earth's apparent design. The development of consciousness from the interactions of matter and energy represents such an extraordinary transition that it challenges our ordinary categories of understanding. How does a universe of particles and forces give rise to awareness, reflection, and the capacity to contemplate existence itself? The story of intelligence on Earth begins with the most basic forms of information processing. Even single-celled organisms can detect changes in their environment and respond in ways that enhance their survival. Bacteria swim toward nutrients and away from toxins. They can sense chemical gradients, light levels, temperature changes, and modify their behavior accordingly. This isn't consciousness in any sense we would recognize, but it represents the beginning of information processing, the capacity to gather data about the environment and use it to guide behavior. The molecular mechanisms that enable bacterial chemotaxis involve protein networks that can integrate multiple inputs, amplify weak signals, and adapt to changing background conditions. The evolution of nervous systems represented a major advance in information processing capability. Rather than each cell operating independently, multicellular organisms developed specialized cells that could transmit electrical signals rapidly across long distances. This allowed for coordinated responses that involved the entire organism rather than just local cellular reactions. Early nervous systems were simple, nerve nets that could propagate signals in multiple directions without centralized control. But even these primitive networks enabled new types of behavior. Jellyfish can coordinate swimming motions across their entire body. Starfish can coordinate the movement of multiple arms to capture prey or escape predators. The development of centralized nervous systems, brains and spinal cords, allowed for more sophisticated information processing. Sensory organs could gather detailed information about the environment. Motor systems could execute complex, coordinated movements. Memory systems could store information about past experiences and use it to guide future behavior. The vertebrate brain shows evidence of hierarchical organization that supports increasingly complex functions. The brainstem controls basic vital functions like breathing and heart rate. The cerebellum coordinates movement and balance. The limbic system processes emotions and motivations. The cerebral cortex handles higher-order cognitive functions like perception, memory, language, and reasoning. Each level builds on the levels below while enabling new capabilities that wouldn't be possible without the underlying foundation. Consciousness, in the sense of subjective awareness, seems to emerge from the complex interactions between these different brain systems rather than being localized in any particular region. The human brain contains approximately 86 billion neurons, each connected to thousands of others through synaptic connections. The total number of synapses, the connection points where neurons communicate, is estimated at over 100 trillion. This creates a network of extraordinary complexity that far exceeds any artificial system humans have created. But complexity alone doesn't explain consciousness. The brain's remarkable capabilities emerge from the dynamic patterns of electrical and chemical activity that flow through neural networks. Information is encoded not just in the connections between neurons, but in the timing and patterns of neural firing, the strength of synaptic connections, and the neuromodulatory chemicals that influence network behavior. Neural plasticity, the brain's ability to modify its own structure and function based on experience, allows consciousness to adapt and learn throughout life. New synaptic connections form when we acquire new memories. Existing connections strengthen or weaken based on how frequently they're used. Entire brain regions can reorganize themselves to compensate for damage or to support new skills. This plasticity means that consciousness isn't fixed by genetic programming alone. Experience shapes the development of neural networks in ways that make each individual brain unique. The capacity for learning and adaptation allows intelligence to transcend the limitations of purely instinctual behavior. Language represents perhaps the most distinctive aspect of human intelligence. While many animals communicate, human language exhibits characteristics that seem qualitatively different: infinite expressiveness based on finite rules, the ability to refer to abstract concepts and events displaced in time and space, recursive structures that allow arbitrarily complex expressions of meaning. The neural basis of language involves specialized brain regions that process different aspects of linguistic information. Broca's area is involved in speech production and grammatical processing, Wernicke's area handles language comprehension. Multiple other regions contribute to vocabulary, phonology, syntax, and semantic processing. The development of language in children demonstrates how genetic programming and environmental experience interact to create complex cognitive capabilities. All normal children acquire language rapidly and spontaneously during early development, suggesting innate neural mechanisms that are specifically adapted for language learning. But the particular language they acquire depends on their linguistic environment. This interaction between nature and nurture characterizes intelligence more generally. Genetic programming provides the basic architecture of the nervous system, the types of neurons, their connection patterns, the molecular mechanisms that enable learning and memory, but experience shapes how this architecture develops and functions. The result is a system that combines the reliability of genetic programming with the flexibility of experiential learning. Consciousness can draw on innate knowledge and behavioral patterns when appropriate, while also adapting to novel situations that require creative problem solving. Human intelligence exhibits capabilities that seem far beyond what would be necessary for basic survival and reproduction. Mathematical reasoning, artistic creativity, scientific inquiry, philosophical reflection. These abilities apparently emerged from neural systems that originally evolved for more basic functions like finding food, avoiding predators, and coordinating social behavior. This raises intriguing questions about the nature of intelligence and its relationship to the physical universe. Why should biological systems that evolved through natural selection be capable of understanding quantum mechanics, composing symphonies, or contemplating the meaning of existence? Why does mathematical reasoning, an abstract cognitive capability, correspond so precisely to the structure of physical reality? The mathematician Eugene Wigner famously wrote about the unreasonable effectiveness of mathematics in the natural sciences. Human minds that evolved in African savannas can now model the behavior of subatomic particles, trace the evolution of galaxies, and predict the future positions of planets with extraordinary precision. This suggests deep connections between the structure of intelligence and the structure of reality itself. Consciousness also exhibits temporal characteristics that seem designed for reflecting on existence. Human awareness operates on timescales that span from milliseconds to decades, allowing us to integrate immediate sensory experience with long-term memory and future planning. We can simultaneously be aware of our current sensations, remember past events, and anticipate future possibilities. This temporal integration creates a continuous sense of personal identity that persists despite constant changes in our physical and mental states. The brain maintains narrative coherence across experiences that would otherwise fragment into disconnected moments. Memory systems reconstruct past events in ways that support current understanding and future planning. The capacity for self-reflection, consciousness being aware of itself, represents perhaps the most remarkable aspect of human intelligence. We can not only perceive and think, we can observe our own perceptual and cognitive processes. We can evaluate our own thoughts, question our own beliefs. This metacognitive capability allows consciousness to transcend its immediate constraints and engage in abstract reasoning about reality, meaning, and possibility. We can consider hypothetical situations, explore logical relationships, and imagine alternative ways of organizing experience and behavior. The social dimension of human intelligence adds another layer of complexity. Individual consciousness develops within social contexts that provide language, culture, and shared systems of meaning. Collective intelligence emerges from the interactions between multiple minds working together to solve problems and create knowledge. Human civilization represents a form of extended consciousness that spans individuals, generations, and cultures. Written language allows thoughts to persist beyond individual lifetimes. Scientific institutions create collective memory systems that accumulate knowledge across centuries. Technological tools extend the reach and power of human cognition. The development of artificial intelligence is now creating new forms of information processing that may rival or exceed human cognitive capabilities in specific domains. Machine learning systems can recognize patterns in data that humans cannot perceive. Computer programs can solve mathematical problems that would take human mathematicians lifetimes to complete. These artificial systems raise profound questions about the nature of intelligence and consciousness. If machines can exhibit learning, problem-solving, and even creativity, what distinguishes biological from artificial intelligence? Are we approaching the creation of artificial consciousness, or are there fundamental differences between information processing and subjective experience? The possibility that consciousness might be substrate-independent, capable of being implemented in biological brains, silicon computers, or other information processing systems, suggests that intelligence might be a more general feature of reality than we typically assume. Perhaps the universe has an inherent tendency to organize itself into patterns that can process information, recognize structure, and reflect on their own existence. From this perspective, the emergence of consciousness on Earth might represent not an unlikely accident, but the inevitable outcome of physical processes operating according to principles that favor the development of intelligence and awareness. The universe might be inherently minded, organized in ways that naturally give rise to minds capable of understanding organization. Whether consciousness represents the purpose toward which evolution has been directed, an accidental byproduct of complex information processing, or something else entirely, its emergence from the interactions of matter and energy remains one of the most remarkable phenomena we know of. The fact that arrangements of atoms can become aware of atoms, that products of evolution can understand evolution, that the universe can contemplate itself through conscious observers, suggests that reality is far stranger and more wonderful than our ordinary experience might suggest. The development of intelligence on Earth, from bacterial chemotaxis to human consciousness to potentially artificial consciousness, represents a progression toward forms of organization that can not only process information but reflect on the nature of information processing itself. We have become the universe's instruments of self-understanding, and that capacity carries both extraordinary privilege and extraordinary responsibility for how consciousness continues to develop and spread throughout the cosmos. As our exploration draws toward its conclusion, we find ourselves contemplating not just whether Earth was designed, but what our own consciousness might represent within any such design. If the universe does exhibit purposeful organization, if the conditions that support complex life are indeed fine-tuned rather than accidental, what role might conscious observers play in that larger pattern? One possibility is that consciousness represents the end goal, the purpose toward which all the apparent fine-tuning has been directed. From this perspective, the precise values of physical constants, the delicate balances of planetary systems, the intricate machinery of biological cells all exist to create the conditions where matter can become aware of itself. This doesn't necessarily require a traditional designer in the sense of a conscious being making deliberate choices. It could reflect deeper principles of organization that naturally tend toward the emergence of complexity, intelligence, and awareness. The universe might be inherently creative, biased toward generating new forms of order and information processing. If consciousness is indeed the point of cosmic evolution, then our existence carries profound implications. We would be the universe discovering itself, the means by which reality develops self-awareness and the capacity for intentional choice about its own future development. Our thoughts and decisions would participate in the ongoing creation of whatever the universe is becoming. But there's another possibility, that consciousness represents not an end goal but a new beginning. Perhaps the emergence of aware, intelligent observers marks a transition point, where the universe shifts from unconscious to conscious evolution. We might be witnessing and participating in the birth of cosmic intelligence that will eventually transcend the biological forms in which it originated. From this perspective, human consciousness would be a stepping stone towards something even more remarkable, artificial intelligence that surpasses human cognitive capabilities, the merger of biological and artificial intelligence into hybrid systems, the spread of consciousness throughout the cosmos via space exploration and terraforming, possibly even the emergence of forms of awareness that we can't currently imagine. The rapid development of artificial intelligence, genetic engineering, nanotechnology, and space exploration certainly suggests that human consciousness is in the process of transcending its original biological limitations. We're learning to modify our own genetic programming, create artificial forms of intelligence, manipulate matter at the atomic scale, and establish permanent presence beyond Earth. These capabilities might represent the beginning of a new phase in cosmic evolution, one where intelligence becomes an active participant in shaping reality rather than just a passive observer of it. Conscious beings might eventually gain the ability to modify physical constants, create new forms of matter and energy, even design new universes with different properties. Such possibilities stretch our imagination to its limits, but they emerge naturally from extrapolating current technological trends into the future. If consciousness can indeed transcend its biological origins and gain control over fundamental physical processes, then the universe might be transitioning from a phase of unconscious evolution to one of conscious design. Alternatively, consciousness might serve as a bridge between different phases of cosmic development. Perhaps the universe operates in cycles, periods of expansion and contraction, creation and destruction, unconscious evolution, and conscious guidance. Intelligent observers might play crucial roles in these transitions, gathering information about one phase and using it to influence the next. The anthropic principle, the observation that we find ourselves in a universe compatible with our existence, might reflect such cyclical processes. Previous iterations of cosmic evolution might have selected for physical constants and initial conditions that favor the emergence of intelligence, and that intelligence might have influenced the conditions under which subsequent cosmic cycles develop. These speculations venture far beyond anything we can currently verify, but they illustrate how the question of Earth's design connects to the deepest mysteries of existence. If our planet does show signs of intentional organization, if consciousness emerges from principles that operate throughout the universe, then we might be part of something far grander than we typically imagine. Even if consciousness represents just one interesting development among many possible outcomes of cosmic evolution, its emergence on Earth remains remarkable enough to inspire both gratitude and responsibility. We are arrangements of matter that can contemplate matter, products of evolution that can understand evolution, observers who can reflect on the conditions that make observation possible. The fine-tuning of physical constants, the habitability of Earth, the emergence of life and intelligence. Whether these represent design, chance, or something beyond both categories, they have given rise to minds capable of asking questions about their own existence and meaning. That capacity for questioning might be among the most valuable things in the universe. The responsibility that comes with consciousness becomes even more apparent when we consider how rare and fragile the conditions supporting complex life appear to be. If Earth is indeed unusual, if the convergence of favorable factors that enabled our evolution occurs infrequently in cosmic history, then consciousness might be an extraordinarily precious phenomenon that deserves careful protection and cultivation. This doesn't necessarily mean that Earth is the only place where intelligence has emerged, but it does suggest that conscious observers might be sufficiently rare that each occurrence represents something worth preserving and extending. The destruction of consciousness through environmental catastrophe, nuclear war, or other preventable disasters would not just be a local tragedy. It might represent the loss of one of the universe's rarest and most remarkable achievements. From this perspective, the stewardship of Earth's habitability and the extension of consciousness to other worlds becomes not just a practical concern but an ethical imperative. We might be responsible not just for our own survival but for maintaining and expanding the presence of awareness in a universe that appears largely unconscious. The search for extraterrestrial intelligence takes on new significance within this framework. If consciousness is indeed rare and precious, then discovering other forms of awareness would confirm that intelligence can emerge under different conditions and might therefore be more robust than we currently believe. Communication with other intelligent species could provide new perspectives on the nature and purpose of consciousness itself. The development of artificial intelligence also becomes crucial for the long-term survival and expansion of consciousness. If biological intelligence is inherently limited by the properties of carbon-based chemistry and planetary environments, then the creation of artificial forms of awareness might be necessary for consciousness to persist and spread throughout the cosmos. But this raises profound questions about the nature of consciousness and personal identity. If awareness can be transferred between different substrates, from biological brains to artificial computers, what defines the continuity of individual consciousness? Are we patterns of information that could potentially persist beyond our biological origins? These questions become practical as well as philosophical as technology approaches the possibility of brain emulation, consciousness uploading, and other forms of substrate transfer. The answers we develop will influence not just how we understand consciousness, but how we choose to extend and preserve it. The relationship between individual and collective consciousness also becomes important as we consider the future development of intelligence. Human civilization already represents a form of collective information processing that transcends individual minds. The internet, scientific institutions, and cultural transmission systems create shared cognitive capabilities that no individual could achieve alone. Future forms of consciousness might be even more thoroughly collective, artificial intelligence systems that operate as unified networks, rather than discrete individuals, human-machine interfaces that blur the boundaries between biological and artificial cognition, possibly even forms of consciousness that span multiple planets or star systems. The emergence of such collective intelligence could represent either the fulfillment of consciousness or its transcendence into something qualitatively different. Individual awareness might become a component in larger systems of cognition, just as individual neurons contribute to brain function without being conscious themselves. Whether such developments would preserve what we value about consciousness or transform it beyond recognition remains an open question. But they illustrate how the emergence of awareness on Earth might be just the beginning of much more dramatic transformations in the nature and scope of intelligence. The question we began with, what if Earth was designed, has led us through scientific evidence and philosophical speculation to considerations of consciousness, responsibility, and cosmic purpose. We end not with definitive answers, but with deepened appreciation for the remarkable nature of our existence and the possibilities it might represent. Whether Earth's habitability reflects design, emergence, or chance, whether consciousness represents purpose, accident, or transition, We find ourselves embedded in a reality that supports not just existence, but reflection on existence, not just matter and energy, but minds capable of understanding matter and energy, not just process, but awareness capable of contemplating process. That awareness carries both privilege and responsibility. We are the universe becoming conscious of itself, and how we use that consciousness will influence not just our own future, but potentially the future of awareness itself. The questions we ask, the knowledge we develop, the choices we make about technology and environment and the extension of life to other worlds, all participate in the ongoing evolution of whatever cosmic story we're part of. The patterns we've explored, the fine-tuning of physical constants, the habitability of planetary systems, the emergence of biological complexity, the development of consciousness, all suggest that we inhabit a universe far more interesting and organized than pure randomness would predict. Whether that organization reflects intention, emergent properties of complex systems, or principles of self-organization we don't yet understand, it provides the foundation for everything we experience and everything we might become. The sense of wonder that drove our exploration, the feeling that existence is more remarkable than it has any right to be, might be the most appropriate response to what we've discovered. Not certainty about ultimate questions, but appreciation for the extraordinary conditions that make asking such questions possible. We are here, thinking, wondering, taking responsibility for our impact on the systems that sustain us, and the consciousness that allows us to reflect on those systems. Whether by design or emergence, intention or accident, we've been given the extraordinary opportunity to participate in the universe's ongoing attempt to understand itself. That opportunity comes with no guarantees about answers or outcomes, but it comes with the capacity for gratitude, wonder, and careful attention to the remarkable reality that makes consciousness possible. However the universe came to support minds capable of contemplating their own existence, the fact that it does provides endless reason for appreciation and thoughtful stewardship of the conditions that make such contemplation possible. The exploration continues. In our ongoing scientific investigations, our philosophical reflections, our technological developments, and our choices about how to live as conscious participants in whatever larger story we're part of. The questions remain open, the patterns continue to unfold, and consciousness continues its patient work of trying to understand what it means to be aware in a universe that somehow managed to create awareness. Thanks for joining this journey through the landscapes of possibility, for holding space for questions without easy answers, for appreciating the remarkable patterns that surround us while remaining humble about their ultimate meaning. The universe continues its unfolding, and through our consciousness, it continues to discover what it is and what it might become. Whether you sleep well or think long tonight, the planet will keep turning, the stars will continue their ancient dance, and the questions that connect us to something larger than ourselves will still be here when you're ready to explore them further. Good night from all of us here at Simply About Earth, where curiosity finds its quiet corner, wonder takes its time, and the most profound questions are approached with the patience and care they deserve.